Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru dunia berbeda, berbeda mana di Samangkara, mana di Samangkara. Batamu lawanlah Adinda, Adinda iman di dadara, Samalaya iman di dadara, Samalaya. Sayang si patoka makai go tego gorokan sayang si patoka makai go tego gorokan sayang sajojo yumadam komi sabapare samuna keke samuna keke soleram anak yang manis janganlah dicium sayang kalau dicium merah pipinya kampungan jauh di mato kunwangsan sebaku liliang takkan aja kawan lamu sangke basuh yang surya.
Indonesia dengan ini menyatakan kemerdekaan Indonesia hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru dunia berbeda, berbeda bagaimanapun di Samangkara, bagaimanapun di Samangkara. Bertemu lawanlah adinda, adinda iman di dada rasa Malaya, iman di dada rasa Malaya. Sayang, sayang, sifat tokaan matego, tego, gorokan. Sayang, 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 sifat tokaan matego, tego, gorokan. Sayang, sajojo, sajojo. Yumadam ko bisa berpari samuna muna muna keke, samuna muna muna keke. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium merah pipinya. Kampungan jauh di Mato, Kunwangsan sebeku liliang, takkan ajo kawan-kawan nalamu, sangke basuh yang suria.
So, hello. Yes, nice to see everyone here already in the Zoom meeting. So, good morning and good afternoon, everyone. On behalf of all the organizers, we thank you very much for joining this workshop. And I'm Nugraha from Research Center for Quantum Physics, National Research and Innovation Agency, or usually called BRIN, Indonesia. It's a great pleasure for us to co-host this event along the International Center for Theoretical Physics, or ICTP, also with University of Indonesia and Institute Teknologi Bandung. Enjoy this workshop, which consists of 3 days, and each day will be around 5 hours, and it's already with 1 hour break. And yeah, let me briefly introduce the background of this workshop to open this workshop, and also introduce you to the organizer, and also remind you some important information related to this workshop. So first of all, this workshop was proposed last year in 2023 when ICTP opened a call for programs for the year 2024. And at that time, some Indonesian condensed matter physicists, including myself, thought that it would be nice if in Indonesia we could make a workshop that teaches us how to use machine learning in physics research. And the main background was rather practical, as you can see in this slide, that we are facing kind of materials revolution supported by powerful simulation techniques, computing power, as well as machine learning. And in Indonesia, or more generally in the global south, we are still considered developing countries. And there are not so many physicists working actively in this field, actually. So therefore, we think that making an online workshop that would invite some experts and contributions from all over the world on these specific topics would be a good idea. And furthermore, some of you may have known that next year, 2025, is designated as the International Year of Quantum Science and Technology by the United Nations. And in our institute, we also try to work on 3 big fields related to quantum science and technology, from quantum theory, quantum materials, and also quantum technology. And quantum materials here, which become the playing ground of most of condensed matter physicists in the world right now, are very central in this regard, because history has shown that each age could be identified by the materials the people in every civilization have used. For example, from the Stone Age, at that time, our ancestors used mostly stone. And also in the Iron Age, most of the people at that time used stone, stone, iron, stone and iron. And then recently we have the Silicon Age, and we use silicon. So with the quantum age in the near future or in the far future, I don't know, it's necessary for us to prepare a quantum ecosystem focusing on the quantum materials. And we can say that the discovery and simulation of various quantum materials could be accelerated by the machine learning. So that's kind of long background, eventually, that now we have this workshop that you are attending right now, which is the ICTP workshop on classical and quantum machine learning for condensed matter physics. Well, now I just would like to introduce briefly about the main organizer of this workshop. So we are from BRIN, as I said before, the National Research and Innovation Agency in Indonesia. And this agency was established in 2021 by merging various institutions in Indonesia in the ministerial and cabinet level. And we currently have around 14,000 staff, with 8,000 researchers working in various fields, from the hard science to the social science. And our structure is something like this. The chairman is kind of Ministry of Science and Technology in other countries. And below him, there are several managerial levels, such as deputies, bureaus, and we also have research organizations and research centers for the research activities. And related to this workshop and also ICTP, our deputy chairman for Human Resources of Science and Technology was the one who signed an MOU with ICTP very recently, and you can check the information from this webpage. And my research center itself, which is one of the 85 research centers in this institute, is one of the active users of this ICTP cooperation. So that's why we can be the host of this workshop. So here is a short introduction to our research center. We are officially named as Green Research Center for Quantum Physics. This research center consists of 7 groups, and those directly related to condensed matter physics and also quantum technology are at least 4 groups: the quantum matter theory group, the quantum simulation group, quantum information and computation group, and the quantum devices and technology group. So we currently have 35 researchers, and most of them already hold PhD degrees, and some have been awarded various awards, such as Habibie Prize, which is the highest scientific award in Indonesia. And there are also some active collaborations that we currently have with international institutions, such as CERN and some universities worldwide. So with the organization of this workshop, we hope that we can also open further collaboration with all of you. So please check our website for further information. And yeah, now it's almost final note for this workshop. We would like to advise all of you, especially students, to be very active in this workshop. In our notes, there are 391 registered participants. This does not count for keynote presenters, which are out of this participants list. But yeah, this 391 already included the 10 contributing speakers. And we will also have 2 hands-on sessions during these 3 days of the workshop. And there are already some questions about the schedule, but if you check this website carefully, and you can also scan by this QR code, you can find the detailed schedule there. But don't forget to convert to your own time zone, because even in my country, there is already somebody who tried to enter Zoom meeting from 10 a.m. in this morning, but it was 5 hours earlier. So don't forget again to convert to your own time zone, okay? And we also put there in the website the materials of this workshop, including the abstracts and the information of the speakers and so on. So also for students, please don't hesitate to ask questions, especially to the keynote presenters, because we will have 30 minutes for each keynote presenter for the discussion. 1 hour presentation plus 30 minutes question and answer should be very good time for students to learn many things and also to ask questions. And if you are not satisfied with asking directly in the Zoom meeting, you can also use Discord server that has been created for this workshop for 3 days only. And please discuss on the relevant channels. So we have created some channels for each talk, and you can discuss with other participants as well as with the speakers. So you can again scan this QR code if you still don't join the Discord. And some of you have also reported through email that you cannot join the server either by the reason of the link is already expired or something else. But I think the main reason was that you still did not make the Discord account. So please make the Discord account first, and then you can click this link and you should be automatically joined, because I have set this link to be infinite in the time. So that means there is no expired date unless we stop it. So yeah, please try again for those who still could not join the Discord server. And yeah, regarding the certificate of participation, it is required for everyone who needs it to attend the Zoom meetings at least more than 50%. So it's about more than 6 hours, because the workshop every day consists of 4 hours if we do not count the break. The break is 1 hour, so 4 plus 1 is 5, but we just count the 4 hours of the exact presentations time. So please join more than 50% or more than 6 hours if you need a certificate of participation. And lastly, we would like to thank everyone who has been involved in this workshop. And particularly here, the first one is the ICTP Senior Coordinator on Programs and Advancement, Professor Ralph Kaiser. He was the one who allowed this proposal to be accepted by ICTP, and also we are deeply grateful to ICTP Secretariat for this workshop, Ms. Victoria and Mr. Hasan Ali. And from our own sides, as the organizer, we have some staff from Green Research Center for Quantum Physics, Dr. Sasvan and friends. And also from ITB and UI, we have Professor Nugroho and Professor Majidi, who have been the main advisors of this workshop. And of course, this workshop could not happen without the support from all the keynote speakers and contributed speakers, and also all of you as the participants. So thank you very much for joining this workshop, and we really hope that you can enjoy this workshop. And sorry if I cannot mention everyone to be thanked in these acknowledgements. And now, also the important part of this workshop, we would like to take a group photo. So group photo means that all of you are kindly requested to open your videos so that we can take screenshot slide by slide. And there are around now 239 participants online. So hopefully we can take the screenshot of everybody. So please open your camera. And I will stop share. Right? So now we are changing to the gallery view. There are at least 5 slides for those who have already opened the camera. Oh, now 6 slides. So let's take one by one. Okay, let's start. 3, 2, 1. That's the first slide. Okay, so give your best smile. Then now the second slide. 3, 2, 1. Okay, third slide. 3, 2, 1. And then the fourth slide. 3, 2, 1. Fifth slide. 3, 2, 1. Okay, almost the last slide. Oh, now there are 7. Okay, no, it's just 6. The sixth slide. 3, 2, 1. And finally, the 7th slide, the last one. 3, 2, 1. Right. Okay, we have taken all of the photos and screenshots of your faces. So hopefully you will enjoy this workshop. And now we will move on to our first keynote presentation. And I will be the moderator also for the first one, as well as the first contributed talk. So for the first keynote presentation, we already have now in the Zoom meeting our distinguished speaker, Professor Ming Dali from MIT, Massachusetts Institute for Technology. Hello, Professor Mingda.
Hello.
Hello. Oh, nice to see you. It's very early morning there, right? In Boston time.
It's 4 o'clock in the morning.
4:15 maybe. So thank you very much for your availability. And now you can start sharing your screen, right? And in the meantime, I will briefly introduce you and also read your brief bio to the audience. So Prof. Mingda is currently an associate professor at MIT, where he belongs to the quantum measurement group and also Department of Nuclear Science and Engineering. He obtained his PhD from the same department, Department of Nuclear Science and Engineering, MIT. And I actually know him, although not directly met him in person, from the interaction with the late Professor Millie Dresselhaus. And if I'm not mistaken, she was one of your advisors, right?
That's right.
Yeah. So that's very nice to know you, and we might be on the same line of academic advice. So until now, he has received some awards to his name, such as the Junior Boss Award, MIT School of Engineering, and also U.S. Department of Energy Early Career Research Program Award, and so on, many awards. And he has also published so many influential papers related to especially quantum materials, and very recently to the machine learning. He has a lot of contributions. So we are very excited to listen to his presentation, which is entitled Characterizing Quantum Materials with Integrated Experiments and Machine Learning. And all of you, all the participants, audience, can read the abstract in the ICTP website or in the Discord server. And if you would like to ask a question to Professor Mingda, we will have time around 30 minutes. So yeah, 1 hour from now. So I will remind Prof. Mingda if it's already 1 hour for your presentation, and then we will continue with the Q&A session for around 30 minutes. So I think that's already enough for the brief introduction. Professor Mingda, are you ready?
Yes.
Yes, so thank you very much. So please start your presentation and we will actively listen to your presentation.
Thank you, Nugrahas, Professor. One question, can you see my screen?
Yes.
Wonderful.
It can be seen clearly, yeah.
Thank you for the very kind introduction, and thank you everyone for attending. Good morning, good afternoon, good evening, and also good night. Today, it will be really great honor and pleasure to share our recent thoughts on how machine learning can play a positive role in characterizing quantum materials. Especially for quantum materials, you think about the interaction between all the charge and the spin and the lattice orbital, all the different degree of freedoms intertwined together. And what we think one possibility is to integrate machine learning together with experiments, which are some kind of the superior court to determine how these quantum materials can behave. So to start, I want to give these two very brief and probably very familiar examples, the materials importance for the future technology. One of the examples is like a giant magnetoresistance, the very simple discovery in the late 1980s. Just imagine if you have two these magnetic layers separated by one non-magnetic layers. When the layers are like a parallel or anti-parallel to each other, then there are order of magnitude difference between this resistance. So that's one effect that drives this hard drive and this capacity increase in the early 2000s. And that's also the reason Alfred Ferd and others won the Nobel Prize in about 27. And the other thing, more recent examples on the blue light LED, it seems also a very simple materials innovation and just try to emit in the blue light. But turned out that this lighting is very critical for this global its energy. Imagine all this 20% of all this energy electricity is used for lighting, and that has been awarded for another Nobel Prize in 2014. So thinking about how this quantum effect and can play a role for this future technology, there are still actually challenges which we think that even those fascinating effects are not that enough to promote for the future. A few really challenging problems. The first one is about the waste heat. So the figure you see here is about the so-called this energy the flow in the United States. On the very left side, there are different types of energy sources. They can be like some fossil fuels, like the petroleums, the natural gas, or they can be from some very clean energy like solars. And after they disperse into different sectors from like a residential to industry to transportation, and end of the day, about 1/3 has been used as a service, and 2/3 are actually wasted as waste heat. And then how people can really reutilize the waste heat into electricity, still an unsolved but ongoing issue to be there. The other thing is also related to the future energy consumption and computing, where this material innovation is definitely needed. So this is a report and performed about in 2015. By that time, thinking about this Landauer limit, which is just individual devices, to this whole system level of this energy consumption for the computing and by the function of year. So what they mentioned is really this daunting figure is that by about 2040, if this computing need for the energy consumption keeps growing, by about 20, 30 years, they will just hit the entire global energy production. And this is really probably not taken very seriously because the energy cost for computing cannot really take a whole global energy production. But if you really look at what actually been happening, imagine our daily life has been improving, a lot of more like online streaming, gaming, and these days large language model and machine learning. So actually the energy cost for all this is actually rapidly increasing for the computing side. About currently, the data center for like a large language model and others consume 1% of the entire energy, this electricity production. And in about 2030, actually 8% of the electricity will be used to power all the data centers. About this is from a report from Nature just a few years ago, and it's still increasing. Roughly follow the trend for this kind of exponential growth. And then, is there any way to really accelerate the materials innovation and to try to solve all the energy and computing crisis? And that is one reason why the machine learning in the past few years has been really playing a very good role for material research, material design, especially for quantum materials. So you can see that in some other fields like biology or even energy materials like lithium-ion batteries, this kind of the machine learning has been really, really successful. They can identify new pharmaceutical molecules, like new these battery materials, new electrolytes. But what are the possible challenges for quantum materials? So here, we'll be happy to provide a slightly different perspective. but by decomposing the challenge into the three, not necessarily orthogonal, but sort of this kind of the axis. The first one is related to the data volume. For many things, other fields like all these molecules, biopharmaceuticals, they really have a very high data volume. The high it means close to the origin. It's kind of easy. But for quantum materials, we imagine have much fewer candidate materials. And that's not the only one challenge. There are other challenges, such as also we can talk about this quantumness or the other things. So thinking about some most ultra quantum materials like quantum spin liquids and others. So people have to use some very extremely computational cost approaches like a quantum Monte Carlo that scales with n to the sixth order, or even exact diagonalization with exponential growth. So that is more like a post-density functional theory, and which is very successful for single particle weak correlated system, but failed completely when we go to really quantum and quantum. And that's why for the energy materials, when people are thinking still about a weakly correlated electron transport or the ionic transport, and that can be very successful, even the data volume is low, it becomes still manageable. The other thing that to describe the quantum materials is a challenge for the dimensionality. Imagine ultimately quantum materials are characterized by the wave functions, which is kind of the exponentially growing if we have the increasing Hilbert space. But that is not good and to really store any useful information. And that's why, and we really want some kind of the low dimension, like effective representation to characterize the key features to describe the quantum materials properties. So if we look at the entire this figure here, imagine that if we have the problem you want to study for machine learning for quantum materials, the closer to origin, then this the more likely you can succeed. And because you can get a higher data volume and a more accurate way to simulate. And then if you have a lower dimension, like even the simple classification problem, and then you probably better can do that. The challenge, and in one sentence, because many problems, it really have a very far distance to the origin. So today's presentation, we're really happy to provide a few of our recent efforts and how to address the challenges. So the trick or the rule of thumb is very simple. We don't want to stay far away from all the three axes, at least stay close to one axis and close to the origin in either X or Y or Z directions. So the first example is very simple as a starter appetizer. It's just use a simple spectrum called X-ray absorption to determine the topological class of these materials. So you can see this is just a classification problem. We are not seeking for higher representation, which we have other examples. And this is also some weakly correlated systems, and then with a relatively high data volume. That's why that becomes one of our early examples. Not that early, but still like 2 years ago. So the motivation to drive this study is really about the utilization for topology. So people are thinking about like a room temperature superconductors and many fascinating quantum materials. But actually, topological materials are actually closer to market than many other quantum materials, with very really promising applications. For example, one, and which is the so-called quantum North Hall effect. So imagine when that happens, you have really dissipationless and this chiral and spin polarized edge currents, and at a higher and higher temperature these days. The other effects become really interesting is a so-called topological diode. So imagine if you want to build a solar cell, let's use a PN junction. So that's like a conventional diode. But for this topological, this Barry curvature dipole, they can also form a diode. But unlike the conventional PN junction, anything below the band gap, you cannot harvest the energy. And here it is possible to harvest the energy and anything like even below the band gap, which means from DC to kilohertz to megahertz to gigahertz, like a Wi-Fi, you can harvest the energy from Wi-Fi to terahertz all the way to the optical frequencies. That sounds a little bit crazy, but that's actually happening also at room temperature. So the other thing is related to the waste heat recovery. So why is it so hard? Because in that field, you imagine you want to tune the materials, like tune the Fermi level or tune this carrier density. Whenever you have a higher and higher charge density, the electrical conductivity, and that will keep increasing. You have more charge carriers, that's good. But then on the other hand, due to the reduced entropy, the thermal power will actually reduce. So that's how much power you can actually get from that effect. The so-called power factor is a kind of the product between these two, and that will have a peak. So interestingly, for all these topological materials, due to all the topologically protected all these states, you can maintain very high this conductivity while getting very high thermal power. That's why people have been showing that this power factor can break the best thermoelectrics by order of magnitude. So that's why these topological materials may play a role for future computing and also semiconductor technology. But what's the challenge? So in just a short one sentence, topology is more like a mathematical concept rather than some directly measurable like electrical conductivity. So this is the one typical workflow to measure topology by using this so-called RPES, angular resolved photo emission typo here. Sorry for that. And the idea is that so whenever you can measure this single particle, the band structure directly, then here is an example for this topological wire semi-metal, which they showed many applications in the previous slide. And then by comparing that with density functional theoretical calculations, you can identify all these topological singularities directly. By doing this kind of the comparison, and then you can identify, hey, there's a topology there. But the limitations are also pretty apparent, and no offense for anyone else doing this RPES. Imagine you have to really cleave the sample to the atomic sharpness and perform these measurements and ultra high vacuum. And then it's really limited what kind of materials can actually be measured and with very high technical barriers. Is there any approach in which you can really simplify the process to measure topology without going through all this high vacuum and all this sample cleavage? That could be the possible, which is the so-called X-ray absorption. One way to think about that is kind of the half RPES. The RPES is like the photon comes in and the electron comes out. The X-ray absorption is like a half in the way photon comes in, being absorbed, and nothing comes out. And the RPES has been traditionally widely used in bio and energy materials as some kind of the chemistry probe. Because if you change the incident X-ray energy to some specific X-ray absorption edge for the given element, and then what you see, no matter the dense regime or the exact regime, is really about the local chemical environment. So like the oxidation state or how many neighbors you have and near the certain atom, information like that. So that's not quite the material, this is for quantum materials probe. But how about if we have machine learning try to interpret the data for the X-ray absorption? So that's one approach have done by my former student, Nina, and to try to use X-ray absorption as a simpler probe to identify topology. So the first thing is to try to build this representation, which is the structure for the data. Imagine if you have any kind of materials coming in, and one axis is certainly different samples. And different samples, you just contain different elements. And for different elements, from the hydrogen to very heavy elements, you have another axis. And then for any kind of the elements, and you have one kind of this, if you have a certain element, the spectrum is turned on. That's why if for this one is like this superconductor material, then it contains 4 different elements. It should have 4 different absorption spectra. And this kind of the high dimensional structure forms the foundation. And then after, if you pass through like a neural network with a different convolution layer, try to consider that as some kind of a nonlinear compression process. And then finally, you can build a classifier, try to predict what topological class for that material and that may belong to. And here are the general behavior for all this kind of the main results. So in general, the feeling for us later as a lesson to build any kind of the machine learning is to always start from like linear classifier. The linear classifier, like this principal component analysis, will build a feeling for how this data will generally behave when they independently and linearly depending for each other. We found something quite interesting and already non-intuitive is that for some materials like the containing aluminum or the silicon, the performance can be really, really good. For some other materials containing some transition metal, the performance, the overall accuracy can be really, really bad. And we want to find out why, and we want to see whether there's any way to go beyond like some these results. And certainly that's limited not only for the binary classification, but some like a topological semi-metal, the TSM, or the topological insulator, and ultimately, and that can be built and to overall this 90 this accuracy from the 90%. And then from there, it becomes possible to not only build the classifier itself, but try to screen some new topological materials. So back then, and we were also trying to see that because of the database was just generated by pure computation, even they represent the local structures, can we really apply them and into some experimental discoveries? So we performed that also on some experimental data and using experimental X-ray absorption. Varying all these this parameter in the Hamiltonian, and then add noise and smearing, and then eventually all this kind of the data and computed this experimental spectra from the quantum transport, and eventually they are all labeled by the topological classes, and either coming from the topological Majorana zero modes, which is this kind of the bound states, or from some kind of the trivial modes. Eventually, and then you can build a classifier from some very simple classifier to the nonlinear classifier and to see whether this is a machine classifiable problem. That is a very natural starting point. But what we wanted to do is one step further in the way to prove this is actually a machine classifiable problem. So how to do that? One approach to see is the so-called topological this data analysis. So that has nothing to do with the topological materials, but really try to build this global data feeling and how different data points are connected. So thinking about you have a Hamiltonian. That Hamiltonian is generated by many parameters, and that's like each data point in this kind of the figure. And now what you can do is to really try to increase the threshold, like try to perturb each parameters and see the connectivity and into these different data points. So imagine that if when you try to change the threshold of all these parameters and different data are started to connect to each other, like if you form the different data points, imagine they live in a high dimensional parameter space. Whenever they form like a circle, then it's like a ring and they are called like a feature 1, or they form like an empty this ball called feature 2. And all these kind of the features you can grow and you can die out. And when you change this all the threshold, And then you can see from here, and this is a global feature for all these spanning different parameters for the topological class containing Majorana zero modes and all the trivial classes. The global behavior are actually quite different. So that shows a strong evidence. So no matter what a particular machine learning algorithm we implement, so that means this is actually a machine classifiable problem. So that builds the confidence for us to really apply different machine learning, even from the simple one to the most involved one, to perform this kind of classification. A few main results are shown here. Still, we also always want to start from this linear classifier, and this PCA here are just a data visualization and try to gain some intuitive sense and how this separability and of all the different data in this different parameter space and are separated from each other. Turned out, and in some cases, even they have a topological class, even linear classifier can give a very good this performance. But and if you have some kind of the topologically trivial class, it can be very bad in classification. So that means that it really needs the connection between these different these data points to convolute all together. That is also very different in the way for human beings to analyze experimental data. Imagine if you have experimental data like the tunneling conductance, and what a human being wants to think is some kind of the peak and do the peak fitting and connecting them separately. And when you see a data like that, like XGBoost, and they have a higher like a score from here compared to the linear classifier, that means that in general, a nonlinear classifier, they turn to try to connect the different data points and all together. So that's the way, and you are not only thinking about the peak independently, but the different other points from the experimental data and all together. Eventually, and by noisization of the data, you can reach the robustness. And then because the problem we pick this one due to this good agreement when people believe is the experimental data and also the computational data, the computation can really have the physical representation for experiments. Then after the noisization, and we can show you can use that to apply for this real experimental data from previous literature. So here are some examples we took from the 16 this different data from previous experiment by other groups. And we show that even the model without the additional noise or model with noise, most of the previous published paper, when they claim there are Majorana zero modes, are actually more likely turned out to be from some trivial modes. There are some kind of the cases, and they turn out to favor the topological this Majorana zero modes. And only one case, which is the case 2, and it survived both. And if you really look at our recent paper, and that's the case that paper was retracted. So it had actually very high quality data from there. So that is something and you can learn and from this particular case. Whenever there's also the low data volume, and it's at least possible to spend some effort and to generate more data, and which is also the watershed when the many low-hanging fruits have been picked. Now, after seeing this one scheme, if we stay to the classification, the lower dimension in this axis, and we can still try to push forward in the other axis, what other possibilities are there? The other things is that this classification probably you think too simple because the dimension is too low. If you have a really high dimension input like the experimental data, maybe you can always succeed. So how about some other things? Whenever your output dimension is actually higher than your input dimension, what could we do about that? In this case, the rule of thumb, we are not ready to also go beyond the PFT level. Let's see what we can do at this kind of the level, and still there are many opportunities. So let me just do a little bit of digression to give this background on this graph neural network before we jump into the topic of what we actually did. So imagine that this approach, when people are talking about these different networks and different these talks, and people can know each other, they are connected like social networks. And for the common structures, like the two most famous one, convolutional neural network, which is kind of a more structured or rigid two-dimensional networks, all the one-dimensional recurrent neural networks It can be used for this text-speech recognition. But thinking about the graph neural network is some kind of a generalization of the CNN or RNN, but on the general grade, even in the map or even in some kind of this brainless networks. And that has been very successful to represent molecules and solid in the past few years. And in the way that you can think not a word represent one graph nodes, but one atom, it becomes a very, very natural representation of one graph node. And also all the different interatomic bonding is becoming the graph edges. And then you can think with this kind of the natural connection in the past years, it's really not the surprise to really use the graph node to represent atoms, which is also one thing we were challenging in our latest work. And why does represent this kind of this materials in the graph? There are many also good reasons, because you really can gain the flexibility. So comparing to the graph representation, there are many this earlier representation. There is one example which is also very important, but with some limitation. For example, Coulomb matrix. Imagine in this matrix, you want to use one matrix to represent your molecule. Basically, the representation means what do you want to tell your computer when you input there is one molecule coming in. The matrix contains the diagonal component, and that is like this just some self-interaction. They also have this Coulomb interaction between these different all these atoms. And then for the two different atoms, you can really calculate the distance by diagonalizing the matrix and calculating all the eigenvalues. So that means that if two different materials, they have different Z, but they can be very different, like sodium, chlorine, they are close to each other, but chemistry are very different. The graph, on the other hand, gives you huge flexibility. You can choose what features you input into the graph. If you care about the mass, you can use the mass feature to represent that atom, or you can use any kind of the vectors or features to represent that particular atoms. And in the graph, this neural network, the key component there is the graph convolution. So thinking about this convolutional neural network, it's about they have the convolution layer. You have each pixel have some kind of atom and with some kind of the yellow mask, and then just doing this point-wise this multiplication, and then you get to the next layer. And one pixel will connect it to the 8 other neighborhood pixels, and also connected to its own self-interactions. On the contrary, on this graph neural network, what people was doing, if you have some kind of the graph node here, like represented by the atoms and the features, and then you also have some kind of self-interaction and also some kind of the neighbors. But the difference is that you can choose and how many good neighbors you want to have. And then that is suitable for solid because you can choose how many neighbors that atoms can have and perform a similar convolution. That is exactly the key step for any graph neural network in the past few years. First, you have this kind of the feature to represent the atom. You sum over all the good neighbors, maybe within a cutoff radius, and then you can propagate from one layer in a neural network to the next layer. But the limitations, and you can see, and before we move forward, is some kind you can directly use that to predict some kind of the properties. What people have been doing is to really add symmetry into this kind of the graph convolution. Imagine that for the one solid, if you rotate them or translate them, it still represents for the same crystal. And during this kind of the filtering process, you can really choose like some kind of like rotational and also this inverse symmetry. And then in order to pass through the layers, and then this is one example, and you can predict even a whole curve with limited data, like 1,000. And this is the example for like a density of states of the phonemes. Based on that, and people can really predict the properties like the density of states from experiments very fast, even containing a few thousand of the atoms. You can use your personal computer and to run it and just for the pre-trained model. So we're thinking about it in this way, people are comfortable and to use these graph nodes to represent atoms, and then doing all the graph convolution, all the steps we skipped here, and eventually to predict something like a curve. But then in this case, how about some other high dimensional quantities like the phonome density of states? And in this case, And the difference is that the phonon, there are other property like the dispersion. The length is actually depends on the input. The dispersion is like the energy and momentum relation for all the lattice vibration of the phonons. And for like Nm atoms in the unit cell, you actually have 3m modes of the phonon. Just one atom can just move XYZ directions. How to gain that flexibility, which is not encoded in this conventional graph neural networks? So what we proposed earlier and is really the virtual node approach. Imagine that if we can add additional these nodes in the graph neural network, and those nodes are not representing atoms, but represent something else. And this is how many virtual nodes are added there, really depending on the input. But we don't want all these virtual nodes to interfere about the original real nodes and the graph convolution we mentioned in the previous slides. So that's why you have only this unidirectional message passing. Only the real directional nodes layers, they can pass information to all these virtual nodes. The virtual nodes between them, they can also passing information between each other. And then eventually, and all this useful information are stored in the virtual nodes. And then that gains the flexibility. Imagine some properties in the solids, some magnetic properties, optical absorptions. The output dimension will not depend on your input crystals. And then this becomes a general approach. You can just change the output depending on input, not only output a fixed length vector or scalar or some fixed length quantities. So the first thing, we want to start from something simple to try to predict the gamma phonon, this zone center in the Brilliant zone for the phonon energies for the very long wavelength phonons. And here in this simplest version, termed this vector virtual nodes, we just add 3m, that's virtual nodes, to represent for m atoms, you should have 3m, this phonon bands, and into the diagonal directions. And then after all this information passing process, just to encode each scalar into each virtual node, eventually sort them out, and then you get 3m energies. In all these curves, what you see here, all the black curves are from this highly computational cost density functional perturbation theory calculations are considered ground truth. And all these blue and orange curves are from the neural network predictions. And for some simpler materials, they are predicting okay. But then whenever you have some complex materials, even in the best 1/3 top this ternary prediction, it becomes worse. That can also be seen if you take a look at this loss distribution for the complex materials prediction with like more than 50 atoms per unit cell. And then in these orange curves, the loss function tends to be much higher, and even the average phonon frequency it does not fall in this diagonal line, which they should. They should have some fix to improve the quality. The remedy here is that not using the phonon energy as the direct output predictions, but rather using some more fundamental quantities. In the case of the phonon, because they are more like a lattice vibrations, the more fundamental quantity is the so-called this dynamical matrix. Imagine if you have these different atoms, they have the interatomic potentials. Performing from there, you can get all these force constants and also the force constant derivatives. This dynamical matrix is a Fourier transform of all these force constant derivative. And then from there, we can build a whole matrix of the virtual nodes. The size is just like the dynamical matrix, but they have very different meaning. So in a real dynamical matrix, and you are computed from all these ab initio calculations from the DFT, but here all the numbers are filled from the gas, from the neural networks. And then you can see that no matter from all the simple materials in these blue ones, or from some very complex materials, the performance becomes much better. And then what you may want to ask, how about to go one step further, not only predict the phonon energy at the zone center, but also the entire this phonon dispersion relation and for the correct Brilliant zone. Then the key question is becoming how to encode the correct this momentum space, the Brilliant zone, into the real space graph neural network. So one approach, what we did here, is to try to use the lattice translation to generate the momentum and to get to the correct reciprocal space. Imagine if you have one crystal unit cell, and you can shift all these unit cell into all the neighborhoods, like this one Rubik cube, and you can generate all the 27 these neighbors, including itself. For each of the unit cell, and then you can have its own matrix virtual nodes. And then for each of the matrix, this virtual matrix, you multiply by the exponential factor for this translation. Sum them up, you get this k-dependent dynamical matrix. And that's how you can actually predict this phonon dispersion relations in both simple solid and also in a very complex solid with thousands of the atoms in the cell. And you can see later and what's our real advantages from there. So why propose this kind of approach? And when there are already many other approaches like machine learning potential already exists there. One advantage is to use that to predict alloy phonon dispersion, as we can see here from the few examples, even predicting the high entropy alloys with 5 different atoms in this occupying one single site, without adding any additional computational costs. The reason is really about how this approach to represent the atomic features. Imagine in the ab initio calculations, and there's one approach called this virtual crystal approximation, and that contains 2 components. You build a virtual atom, they have this average mass as this average between the atom A and B, and this is just the alloying ratio. And then you also want to build this virtual potential and also as some kind of this average potential between the 2 atoms. And then you substitute all this into the Concurrent equations to rerun the entire calculation to obtain the final results. But here, for the machine learning, this graph neural network approach, you can imagine for each atom is represented by a vector like this. And each component is the type of the atom. The hydrogen, you turn on the first component. Helium, you turn on the second. Then if you have some kind of the alloy, you just turn on the multiple components and all together. This is like the second equation. And then the number you endow into the different components are just the corresponding like a relative this mass ratios. That's why this computational cost when you encode an alloy and encode one this pure material and becomes the same. And in addition to this kind of the alloy, because this approach is purely based on the graph neural networks guess, this skips a few things, including like this ab initio calculations and like the false constants calculation. Even the machine learning interempirical potential, you need to calculate the false constants, and you need to also further perform Fourier transform. By skipping all these kind of steps, it turned out the computational cost can be saved by even another 2 to 3 order of magnitude, like 100 to 1,000 times consistently, even for material containing different elements. So that's why it becomes a very fast approach to calculate phonon dispersion relation compared to ML+IP, and turned out the accuracy is no bad, probably slightly better, but you can see at least comparable to a machine learning mechanical potential approaches. Now you can see that if we can really use like this virtual space to store information, it can also possibly to beat some dimensionality curves to use low dimension input to predict the high dimension output, like the phonon dispersion relation with entire momentum space in 3D and also 3n bands and in this energy space. Anything else that can be done? How about we think about another example related to phonon, but this time with very low data volume, and there's no way also to get to to the high data at this point. So how low would that be? The low is like 1 and without any way to improve. Is there any way to perform machine learning without any data? To give a little background on this particular approach, we want to really learn about this phonon thermal transport. In this community, what people care most are 2 measurables, like thermal conductivity and interfacial thermal conductance. And then that's K and G. They are not the most fundamental quantities. If you are thinking about the kinematic model, they are determined by like a heat capacity C, group velocity Vg, and also the relaxation time tau, or the transmittance T. In our previous work, like the virtual nodes, when you can predict the phonon dispersion relation, you can immediately obtain all the group velocity and also integrate over to get a heat capacity. But the tau and T are some extrinsic parameters you can know by only knowing the structures. They also are related very sensitively to all these defects. That's why if we really ask, can we directly build a structure property relation to predict that? I think it's very hard because we really don't know the detailed defect structures in materials. And even we know and how to compute the scattering is also another thing very hard to get the ground truth. Then can we do the second best thing? Rather than directly learn them from structure, can we learn it from something else, some way, like experimental data? That is some kind of our philosophy to approach this problem. And if we have some kind of this phonon properties, because the structures, they can scatter with all these atomic defects, and you don't even can know all these equations can apply into the equation, the level of validity is also highly unjustified, like this green boundaries, this model. And then ultimately, what we really can do is only the second best thing is try to learn from experimental data. The whole workflow is like this. Imagine if you have some kind of this like bilayer or even multi-layer structure, and you want to study the thermal transport from here. And they are characterized by some relaxation or this transmittance, like modeled about tau. And then you have some kind of the pump probe, and also the pump will heat up the sample. The probe will measure the diffraction patterns as a function of a time delay between the pump and the probe. And then this model contains the two parts. The first, we want to validate that this whole thermal transport process can be described by some kind of the thermal transport equations. In this case, it's not very hard to justify the Boltzmann transport equations, which is largely valid in many regimes, can model this whole entire approach. From there, you can imagine whenever you have a higher temperature, then you have the non-uniform energy distribution, G. And then from there, when the atomic are vibrating faster, you can obtain this intensity, I. And then at the end of the day, what you can do is to get the intensity as a function of time delay. The real challenge is the backward part. If you have experimental data like this X-ray or this electron intensity, how to uncover all these thermal parameters inside all these models. And that will be challenging in a way. This is the yield-posed problem. Whenever the heat dissipates across interface, it doesn't have to go straight. It also scatters into different directions. Turned out it's not one single differential equation, but in this particular case for us, it converged only after 3,000 this partial differential equations to converge. But is there any machine learning approach with this limited data, but assuming it satisfies a transport equation to really uncover some hidden model parameters and inside the whole this system in terms of thermal transport? So to give a little bit more detail on both the forward part and backward part. The forward part, what we wanted to learn is how everything is connected. That's the easy part. Imagine if you have some sample heated up, and then it leads to some energy distribution. For all this energy distribution as a function of position, phonon frequency, and time, you really can learn the local lattice displacement, the atomic vibrations. And that is the general idea, and you can learn from here. And measure the data. If you have a faster atomic vibration, it is smeared out from the bipolar effect, and then it becomes more like a reduced intensity from there. On the contrary, and the backward part becomes more intertwined. So I skipped all that part on this mathematical detail, but you can see from the approach to see how this transmittance and also the relaxation can be recovered from the entire things. All these are as a function of these phonon frequencies. And before performing any experimental validation, we first perform the computational benchmarks. Initially, and we want to do this randomized initialization, so the data are quite noisy. But then even after enough sufficient randomization, eventually, even after just very noisy this data, you can fall onto the ground truth. all the blue and all the orange curves are from the this training, and which encodes the differential equation eventually, and it falls onto the ground truth and for the next transmittance of the phonon and which is what given in this particular materials. By using this kind of the spirit, what we can do is to really apply them into this data from experiments. What we have been studying is just a bilayer structure, is gold on top of a silicon. And the gold serves as the heater and the silicon diffuse the heat. And as a function of all this intensity, you can see the intensity really follows the By-Waller law, dropping as a function of this Q square. And then by fitting all this experimentally extracted this lattice vibration, and eventually, and what you can obtain is the function like this. That is the so-called this spatially distributed and time-dependent and also phonon energy dependent, this whole dynamical process, how phonon relaxes. What is really helpful in this particular process is the co-monitoring between these two layers. And not only the one layer, the time dependence of the diffraction is being monitored, but the two layers are co-optimized at the same time. And for all these reconstructed curves and these computational curves. Imagine in this our particular case, we have just a 5 nanometer thick this gold layer on top of this 35 nanometer silicon. And then after this whole reconstruction process, you can see from the pure experimental data, the only assumption is the thermal transport agrees with, can be described by Boltzmann transport equation. And then what you can get is how this phonon energy distribution, the G function, as a function of the spatial from the gold layer to silicon, and as a function of time, and then how they hit the barrier. Some of them will be dissipated into vacuum, and some of them will be reflected back. And more than that, as a function of different phonon frequencies. So that would be our this fourth example. But before we conclude, what if we run out of all the kind of the options? Because the one thing we couldn't get around is to perform the exponentially high growing this computational cost and really become the challenge in the ultra correlated regime. In the last few minutes, we're happy to really introduce our most recent results on the generative model to generate quantum materials candidates. So in the previous all these few examples, you can consider all the models, no matter classification or the regression, is like some kind of the discriminant model, like just try to distinguish a dog from a cat. The generative model is very different. You can imagine if we have some kind of probability distribution, we want to sample from the probability distribution, and we want to sample to know we want to sample a cat or a dog. Then in the past few years, one of the state-of-the-art approach on the generative model is this diffusion-based machine learning. And in this case, so comparing to some earlier approach like the variation autoencoder or as the adversarial networks, this allows the fine-tune between the different layers. Imagine if you have some kind of original undistracted data like X0. And then what you can really do is the gradual normalization process from like a Gaussian process. Eventually, you turn it into a noise, which is very simple. You can easily turn into some low entropy object to some high entropy object like this. The key here is the denormalization. You want to go from the xt to xt minus 1 layer by layer. Could be thousands of layers here. And that denoise process can be represented by the neural network and can be trained and which parameterized by something you can do from the machine learning training. And then, but the situation is, and we want to generate some quantum materials with specific these lattice types. So why lattice types become something matters? Because that's closely to some kind of this exotic magnetism that this lattice may host. One example is the so-called quantum spin liquids, which has a very promising application, also contains the Majorana modes for topological quantum computation. But the problem is that the true computation, like if they perform this ED calculation, is really exponentially growing high computational cost, and experimental evidence is also very hard. So in the past decade, there are probably only a dozen materials have been identified and also as candidates. But one feature is that geometrical frustration can possibly lead to the quantum spin liquid as a candidate. So which is some kind of the possible necessary but not sufficient condition if you are not talking about interaction-driven quantum spin liquid. Some kind of the triangular or this Kagome or honeycomb lattice, they may have the chance to host a frustrated magnetism, and then from there it could be possible to generate quantum spin liquid candidates. And what we want is to really expand the set from the dozen and to like millions. So assuming, and this is one approach, and just 2 years ago, and try to generate not material but really image. And how to generate image when we have some kind of the constraint. Imagine if there's one part of this image has been just masked, and then the goal is to just generate all this masked part, which could be different, but the key is to make the masked part of the generation and the unmasked part to be seamlessly connected to each other. The whole idea for this kind of the generation is for each layer of the diffusion step, it contains the two parts. For the masked part and unmasked part, they are sampled from the two different distributions. Because we want to smooth this generation, even the masked part, we don't want to pure and sharp image. We still want to gradually normalize them to sample them from a distribution. And then between each layer, we can do this kind of the weighted average, and between each diffusion step to the next step. And then that's how this can be put in together for the masked and the unmasked part. And based on that approach, people have been using that to generate masked images. And here are the few examples shown in that papers and 2 years ago. And by using that approach, what we have been doing is to really generate and materials candidate with certain lattice types. For each kind of the lattice, like if we want to generate the triangular or honeycomb or only the Kagome lattice, we can consider that as part of this kind of the geometrical constraint. And then for each geometrical constraint, we can generate from a perfect crystal eventually to some kind of the noise. And on the other hand, we also have this unconstrained part, which you can freely choose the crystal lattice, the type, and also the unit cell sizes. By merging also these two kind of the constraints, and then eventually what is possible to really generate a new material, but it was guaranteed to fix that particular lattice type. So here are just from some examples, and you can certainly do this kind of the diffusion on the type of the lattice and coordinates, and also type of the lattice can also be changed. The challenge, as you can see, is the kind of this dilemma here. If we want to generate some quantum spin liquid candidates, we want generative models. If we want generative models, and then what we need is that to build the model by ourselves. And normally to build the model by ourselves, we need data. But there is no any data available. So that's why we have to collect the materials and build the database. That becomes some kind of impossible task from the beginning to the end. In order to just to take one step back, not thinking about a quantum spin liquid, given how hard it is to compute or to experiment or validate in any existing approach. And what we were focusing here is just to focus on specific magnetic type of atoms on certain type of the lattices. Imagine here are just two this kind of examples. You started from some kind of the random noise, put this constraint for the geometrical constraint, and at the end of the day, what you can get prototype for like a coupled superconductors. And then based on all these spirits, certainly you can build this very large database. And soon, I think probably in very near future, we'll be releasing this work, and which generated about 8 million of the new materials, and many of them are tested to be stable at the level of density functional theory. So here are just a few examples. Not only the Kagome materials, but also there are some other types of two-dimensional this tiling, and they could also be possibly interesting. Just to give you a few examples belonging to the so-called Archimedean lattice types, or even the so-called Lieb lattice, which can host electronic flat bands. I think my time is up. I'm right on time. A brief take-home message, and whenever there are some kind of the data scarcity or this kind of the dimensionality curves, and how we can perform meaningful machine learning. A few things, whenever there's no any challenge, at least we can identify the suitable problem and with a reasonable this high data volume and ground truth, then to perform some simple tasks. And then if there are some kind of the more challenging problem, you can see that there's a gradual transition. When there are no existing data available, we will be able to generate our own data, which is becoming a general trend. And then what we are seeking for is the problem where this computational data and experimental data can converge, which means computation can at least represent a significant portion of a phase for experiments. And about this high dimension for output challenge, and what we show is to really use the symmetry equivariant neural network and also use the this virtual nodes and to accommodate all these dimensions. And other things besides data itself, it is also possible to use partial differential equations to contain all the data. And certainly, if we have no way at all, no experiment, no computation, at least we can start to generate some data candidates. Hope we'll conclude here for the excitement for the down future. Before I conclude, I really want to thank all my group members and also collaborators, particularly Professor Yuan Hong Sensei and from Tohoku University and many of my funding agencies and to support all the works described. With that, I will stop here. Thank you very much for your attention. I'll be really happy to take any questions in the next half hour.
Well, thank you very much, Professor Mingda, for a very impressive talk and also nice research results. So let's give applause from the audience. And we already have a lot of questions here, Prof. Mingda. So maybe I would select some of them. The priority is for those who already sent some Zoom chats. So first one is short comment from Colin Benjamin. He said that MZN probability never reaches 1. Is it a question or comment, Professor Colin Benjamin? What about you, Professor Ming? The MZN probability never reaches 1.
Yeah, it's both a question as well as a comment. In those Majorana zero modes, the probability of the conductance which we showed never reached 1. So how do you distinguish between the trivial and the topological after the noise and adding them and doing a machine learning analysis? That I couldn't follow. And you put a cutoff actually around 0.7 or something to distinguish between the trivial and the topological. If that you could also explain what is the reason for putting a cutoff like that.
Okay, so please, Professor Mingda, answer this question.
Yes, I think that's a great question. Let me try to rephrase and give me first thing, and you can imagine when you want to describe a problem like that, it's really about how broad you want to distribute all the Hamiltonian parameters, how many parameters you want to include, and for all these included parameters, and including some external parameter like voltage bias or the demand energy, and how many like this like chemical potential and other things, what is the parameter for the entire Hamiltonian. And that has been done in a very broad sense. And being said, for each parameter combination, and you can still confidently compute the topological invariant to obtain the corresponding topological class. But to see a figure like this, the total this probability, and it would be not 1, right? In a way that eventually before the final layer, you always want to have some kind of a smooth function like a sigmoid or the tangent H, and to really try to give a more like intuitive understanding in a continuous way, try to see given this particular set and how much confidence we have and in this particular combination. What can actually be done in this process is not only do the classification, but you can actually learn the parameters. But the question is how to validate the parameters. That is an even challenging problem because the topological invariant you can validate from the top, just calculating the invariant. But if you have the data like this coming in, and it becomes even higher confidence, you have to assert this model can describe the entire system, and then to really describe all the like model parameters. So that's why if you only want to stop here doing classification and doing this continuous probability, that's actually much more like a confident side, because you know you are not carrying too much on the parameter, but only caring about the continuous probability, and you can output a scalar from there, not doing a regression problem, and you will get a probability distribution for each parameter. So I think I probably answered more, but if you get back to the original question, it won't be a discrete number. It will be a continuous distribution and before the final layer.
Okay. So thank you for the question, Colin Benjamin. So I would move on to the next question. Actually, it's very short comment from Gustavo. There is a professor at MIT who is really influential in this area of graph neural network, Tess Smith. Is it correct, Prof. Mingda? Do you know him, Professor Tess Smith?
Yes, I think she is a close collaborator of myself.
Oh, really? Okay, right. That's very nice. So then the next question, still from the Zoom meeting from Edwi Hasdeo. I'm not familiar with GNN for guessing the phonodynamical matrix. What is the input for GNN?
Right. So I think there are two ways to think about the input of GNN in this particular case. And one is just your crystal structure file. If you do experiments, that's the CIF file, and or any like these files when you input for your ab initio calculations. And basically, what are really encoded are two info. And let me just put it here. One is the type of the atoms. And whenever there is a type of the atoms, it's up to you to choose what kind of the features you want to give to the atom. In the phonon case, the input is just the atomic mass. So that is really well known. And the other thing is like the different atomic positions, just like the crystal structure. So that means that how they are really used, there are parts that has a cutoff between the radius. This distance between different atoms are encoded in a cutoff function, and then the relative angles and will be encoded in this spherical harmonics, which are kind of the how to say this angular distribution as a vector and in this encoding. So you can consider in the GNN, it can input general crystal structure, and this is how the general structure will be used, and the distance between atoms and this angular distribution of the atoms and the atom itself are used in different ways.
Right. Okay. So I think it answers the first question, but actually Hasdeo has a second question. What is the typical error in the phonon dispersion, and what is the challenge to get a perfect fit?
Yes, that's a great question. So there are many ways to see the general performance. And you can say that if you want to compute some single scalar performance indicator like average phonon frequency, you can really tailor toward that. Put anything you care into the loss function and it can get really well. But the question is how faithful and do you want to believe that is the answer you want? And in a particular case, and for our example, the training data we took and it's from the database and done in 2018 by the group from the Abinet developer. And they contain a lot of the oxide in the training data. That's why the training data for oxides are always perform the best if it contains oxides. On the other hand, in this case, we just encode the atoms with mass. And that means that if you have some effect that beyond the mass effect, like a hydrogen, and if you have a hydrogen-rich material, like some people care for these superconductors, hydrides, and then it's not only mass effect, but also not only height by frequency, but there are also some other electrostatic effect, hydrogen bonds there. It goes beyond mass, and then this performance becomes worse, which we tested. We think it can be addressed, but it was not the priority there. What was the priority is to, when you have a very fast predictor, to do material search with some superior performance, like thermal storage and high heat capacity, high thermal conductivity, other things. But I think overall, there's in general, this is still loss machine learning, which means when you gain the efficiency, you lost some accuracy, and that's why I still feel ab initio like DFPT are still the best if you really want to know exact and for one particular material, but not try to do material design given 100 material tell which are the top 10 things like that.
Right. Thank you for the answer. And now let's go to the next question from Nasiru. It seems that he just wants to follow up whether we can use what you have explained, Professor Mingda, in 3D materials modeling. I think yes.
Yeah, I would say yes, and certainly happy to talk more what kind of the modeling, but yeah, it should be highly flexible toward the many applications.
And he also asked a question about the can we use this kind of technique when we have several time series input?
I lost the what kind of input? Would you mind to repeat again or?
Time series.
So absolutely yes. And time series, I think for many machine learning frameworks are suffering from this kind of the so-called this vanishing gradient problem. So imagine if your time dynamics is very long, and then if you do like a recurrent neural network, it will just forget what happened before. There are certainly many remedies like this long short-term memory, LSTM, and even this attention network, which provides more powerful approach. So I am not sure. I think it will be problem dependent. If your problem is related to partial differential equations, the approach we used, like scientific machine learning, is really powerful because by applying the so-called adjoint state, you can always guarantee there's a loss function, and even there are ill-posed problem, you can reach to global minima. But if you have other data structures and not a PDE, probably not for the neural ODE approach, not the but I think this attention network and which is the foundation for large language model could be a very natural choice, or start from like LSTM from there.
All right. So okay, let's go to the next question from Reinhard. He asked about how do you produce the noise in one of your slides? Is it a function? And how do you define the cutoff ratio?
Yes. So I think noise, that's a great question. So there are different ways to define noise, and intuitively in many works, and they just put a Gaussian noise on the original data. And then what want to be careful is that assuming you have an experimental distribution and you have a computational distribution, and can the direct adding of the Gaussian noise represent the experimental data? And turned out the answer can be no, because they can be shifted. The reality, and for many real experiment data, works like you have a resolution function from instrument, and then you have the noise from each step of the component of the instrument, and then that instrument resolution function has to take a convolution operation to your genuine this computational ground truth, and then after doing the convolution, it doesn't have to be the same this noise. So I think it's really depending on how well you want to justify and how much effort it can be spent in the particular noise. Some spectra, like X-ray absorption, and people generally agree the computational data can really well represent experimental data, even without any post-processing. So people can overlay computational curve and experimental in one curve. I think that's a good example. You don't need to worry about too much noise, but not for other examples, like even phonon measurements. And regarding the cutoff, I am not entirely sure what are the cutoffs. There are two cutoffs at least. One is a cutoff here, and the cutoff radius. And this one, you don't need to choose a very large number. If you choose a large number, like 6 angstrom, then you include too many atoms. And what you actually wanted to do is to let the information to be able to pass flow from one layer to the other. So as long as each atom you can connect, then it's good. So which means the minimum cutoff is on top of the interatomic this bond distance. So practically, I think the 5 angstrom is more than enough for most of the applications. And if you're talking about a cutoff of the distribution between the training or this validation or this test data, and for many of the examples, we are on the very low data volume side, then you can cut off a lot for training and try to get as more training data as possible, and can deviate from the 80-20 rule. But in general, there are flexibility, and we adopted a more pragmatic approach and to choose other cutoffs, and certainly always do this optimization and hyperparameters tuning and as one necessary steps.
Right. Okay, thank you very much. So now the next question from Mr. Infinix. I'm not sure, this might not be his real name. He is currently studying the electronic properties of silicon when doped with some other group 2 elements. He uses DFT, but the question is, can your approach be adopted, and how? And also, does it have applications for thermal properties of materials?
Oh, that's another very good question. Long story short, the whole approach can certainly be used to study electronic band structures. Probably there are some similar questions on top of that. You can build a direct structure property relationship. You input the crystal structure and output the electronic band structure. And on top of that, because these days also the linearization, automatic linearization are also quite advanced. And it could even be possible you can learn effective Hamiltonian or the Hamiltonian parameters or tight bending Hamiltonians, and from atomic structures directly. That could be another possibilities. And for thermal properties, it's really also depending on to what level we want to accurately describe all that. Because for many applications, like extreme temperature, higher temperature, when like a phono-phono interaction becomes important, and then to calculate this anharmonic interaction will become challenging to even generate the database. But it could also be a very valuable task to do that. But if you really want to do the simple the screen functions calculation to roughly get an idea, that could be still be valuable, and not to say get accurate number for individual material, but more for material screening. If you have 1,000 materials and then you want to know what would be the top 10, top 100, then that could be 70 chance you hit some good examples. And then after the down screening, perform more refined calculation. I think the mindset is slightly different. We're not pursuing and the accuracy for individual material, but more like a massive material design and search.
All right. So thank you for the answer. And now I would like to allow at least one person from the Zoom meeting who would like to ask by audio. So Dr. Sandy, please. You can unmute yourself. Yeah.
Yeah. So thank you for the opportunity to ask. So thank you, Prof. Linda, for the lecture. It's great. A couple of questions from me. So basically, first, a quick check on your XAS paper. Just to confirm that basically you haven't really established the connection between the topology coming from the electronic close to Fermi level and the XAS that you use as your input data. That's the first one. I just want to get a quick confirmation if that's actually the case.
Yeah, that's a very good question. So long story short, I think if you really want to review the topological properties, and the Fermi level location is extremely important, certainly for many other applications. The key here, we have to feed the machine a way to encode the Fermi level. And then if you really look at the examples from all this data and everything here, it's more like a natural representation. It does not tune Fermi level. And then in many later these examples like a phonon, if people only encode the atomic mass, that also does not encode any Fermi level information. And there are certainly a few approaches to try to tune Fermi level, But imagine if we are really sensitive to that, you can put that as another like a label as a kind of the condition, they call the conditioning, and to put another as an input, and which would be one thing. But then the training data has to have the ground truth. It has to contain what the material behaves, let's say topological or not, when they have different Fermi levels. So, but the question is the Fermi level dependent calculation, probably because high throughput on the 100,000 materials have been done already by Nicholas and collaborators. It could be possible, but it also be a very formidable task, I would imagine. But I would fully agree if when that happens, the sole XAS data will not be sensitive. I think that's so true. And then there need another input number, let's say Fermi level directly, and if we want to do in that approach.
Yeah, so then basically to follow up from there, then to put it in another sentence, well, anything, but basically you use this XAS and then you use this to classify whether that's a topological or not topological. Is it then possible, or you may have some comment, is it then possible you are actually capturing something else rather than the topological or non-topological? That's why then probably you got only like 90% accuracy, let's say. Like just wondering whether, yeah, since, I mean, in my understanding, topological property happens on the electron band structure close to the Fermi level, and then now you're looking at the XAS, which is basically like very deep. So my natural kind of like question is, are you actually capturing something else rather than the topological or non-topological property of your electron band structure?
Thank you for asking. That's a great question. So basically, and so short answer is no, because the XAS has already been really very well used in many other fields, like batteries, other many not quantum related research. And the topology is kind of out of blue because this is not a typical probe to prove topology. But imagine in the way that the recent high throughput calculation show like even 50% of all the material are topological, and when they are Fermi level at the topological bands, but then if they contain the one away from Fermi level from there, right, it's like 80%. And so that means that it will face the same problem even if people do RPAS. Because if they do RPAS and they only see anything below Fermi level, and then if you do that, you still miss the materials when the topological bands are above the Fermi levels. So that's why, like RPAS, if we don't have like ab initio then to interpret the data, that still will be problem. In this case, the use is slightly different. If let's say we have 90% accuracy, we really cannot just assert this material is topological and in 100%. But what we can do is that if you have 100 materials, then down selected, they have a high confidence to be topological. And then if some of them are for more interest for any reason, and like some correlation of some interesting geometrical structure, then it's possible to bring in more motivation to perform more refined calculation and for further, let's say, DFT or this or RPAS studies, and because RPAS you just need a powder sample, sorry, XAS, and very easy to prepare anything, even to run the experiment.
Right. Yeah. I mean, if I may, just one more question, not related to this, but it's about your generative neural network. So basically, generative study at the last part of your talk. So I just wonder, sorry. So I just wonder, so if I can like try to kind of like put it in a way. So you're trying to generate what material? But if I understand correctly, the method itself actually try to use some noise, right? So basically, like the training is you have the original picture and then you cut it off, and then you try to train your model to predict what is being missed in here. And so then to relate it to the material, then maybe I missed something in your lecture. So what is it that's being generated in this case? And what is the noise? I think it's before.
I see.
Not this one, I guess. I guess it's before.
Yes, that's a very good question.
Yeah, this one. 48, correct, yes.
Yeah. So you can consider this is the final material you want to generate, and it contains two parts. One is the part you want to constrain, like you want to only have those magnetic items to sit on a certain lattice, like the Kagome lattice. And then this is the pure noise, which you just put a random number of atoms and also the random number of lattice from here. And you ask what are the noise, we imagine all of them, but these two are treated differently. For the constraint part, when you do the normalization, it always started to have all the constraint maintained. And on the other hand, the other channels and it's all like
Login lagi aja. Buka lagi Zoom-nya.
Unconstrained and this part. So if you look at what I showed here, maybe that will be clearer. And each part you have the constraint and also the unconstrained part as a linear combination. And no matter the atomic type, the lattice type, and the coordinates, and they are all drawn from the distribution. Gradually, it's noisier and noisier. It's become wider and wider. Eventually, at the end step, it's a real noise.
Okay. Yeah. Anyway. Okay. Thank you very much.
All right. So thank you very much for the discussion, and we only have 5 minutes remaining. So I would like to select one question from Discord. Prof. Minda, if you still can follow Discord later after this talk, please answer some questions there. One of the question is related to the 19 slide number 19. You talk about 85% noisy theoretical data. What does it mean? This is from Mr. Chandan Kumar Singh.
Yeah, let me first go to
slide 19.
Yeah, that is slide 19. So yes,
85% for noisy theoretical data. So he is asking what's the meaning of this.
Thank you. I think I probably should give a more comprehensive overview of what's happening here. The first thing is that the data, there are two types. One is 2D data, which is like you have a function of the bias voltage and you gate the voltage. And the other is like a magnetic field, the demand this potential. And if you have that kind of the data, which is the whole curve, like you can see here, this is the 2D data. And the 1D data in that overall, this feature is just the one-dimensional curve like this. Basically, you don't screen the magnetic field, you fix the magnetic field, and then try to just scan the bias voltage. That's called 1D data. And then that's the first and second row, 2D and 1D. And within these different approaches, certainly you can start from simple this SVM and support vector machine, or just this clean data, and this clean data added all this noise. And so that is the noisization process. The smearing is actually one additional step during the whole thing. There are some kind of the misclassification. So imagine if you only look at the data at the parameter space, and naively people will think this is a parameter range, and that will give this set of a topological class. A different range of a parameter will give a different parameter range. But it's interesting that there are always some misclassification, and that misclassification has to be taken care of, either just to relabel them using the topological this data and using the correct topological label, and then that's the part. And what we did the step is like the smearing and part, and so it's some kind of the thing, and we can make the this ground truth more accurate. And in the meantime, and we can also just consider this data can represent more faithfully and for the experimental data. And normally you can imagine the performance will drop, and like what you see here. But the robustness and the generalizability will also actually increase, which is a good thing. So we would normally want to do that, even you see the drop, and by doing all that cases.
Right. So due to the time limitation, I will only read two questions, but there are still a lot of questions, and maybe we can discuss furthermore in the Discord. So the last two questions is from Mr. Hakan. Professor Minda, can you please share your thought on how this machine learning work can help to solve synthesis problems that experimentalists face while they fabricate exotic materials?
That's a great question. Happy to chat more. Recently, certainly there are a lot of ongoing effort, like Berkeley's A Lab has been really doing a fantastic job on that. And we are also actually doing something related to synthesis. And so I think two things is how to represent the synthesis, because that is not a scalar, not a vector, but a whole procedure. How to find the efficient representation on the synthesis would be one thing. And the other is related to how to obtain enough critical mass, which means sufficient data for training. But I'd be happy to chat more along that track.
Right. So a very short question, the last one from Dr. Mahbahuddin. He wants to know the space complexity of a graph neural network, vector virtual node, and matrix virtual node techniques. The space complexity.
Yeah, so imagine if you do DFPT, the complexity grows like m to the fourth to fifth order. M is the number of atoms in a unit cell. And in this particular case, the one you see, the virtual nodes and in the graph neural network grows about n to the quadratic order. So that means that if you have 100 atoms, you roughly can see it's 10,000 to 1,000,000 times efficiency saving with a very low prefactor.
Right. So thank you very much for very nice question and answers. But unfortunately, our time is very limited. And yeah, before closing this session, I just would like to share to everyone and also to Prof. Minda that we have a Discord channel here, Keynote 1, Keynote 2, and so on. And for Prof. Minda, the channel is here, Keynote 1. So if you have time, Prof. Minda, during your busy schedule, could you just answer some of the questions that have been raised by the participants? So we would be very grateful if you can answer those questions. And also for participants who already asked some questions in the Zoom meeting, in the Zoom chat, but I could not ask them due to the time limitation, you can please ask again in the Discord server. Okay. So hopefully this can work for everyone. So thank you very much once again, Prof. Minda, and hopefully, yeah, you will have further nice research that can be shared with everyone in the future workshops or conference or any kind of meeting. And once again, hopefully you can answer some of the questions raised by the participants in the Discord server for the Keynote 1 channel. So everyone, let's give applause to Prof. Minda, and yeah, we thank him very much for his availability, although the time in Boston now is still very early morning. So let's give applause for Prof. Minda. Oh, by the way, one question, Prof. Minda. You share the slides to organizer, but is it allowed to be shared to the participants or not?
Yes, I'd be happy to share.
So it's allowed. Oh, okay. So then, yeah, we will give the link to the participants in the Discord server and also in the email. So yes, thank you very much. So see you again. And if you still have time, you could answer the questions in the Discord server and still join this Zoom meeting. So with that, I'm going to close this first keynote presentation. So we will give around 15 seconds for the organizer to stop the recording and then restart the recording, because we will upload this recording to ICTP website later after the workshop is finished. And yeah, please for the organizer. Right, then now we would like to call the first contributed speaker, Dr. Amna Ahmed. Are you already here? Yes.
Yeah.
Yes, so thank you very much for your contribution, and please start sharing your screen and presentation. And in the Discord server, we also have make a channel for you as the contributed one, and your talk will be about the phase classification in disorder quantum systems through machine learning. And yeah, Dr. Amna Ahmed is from University of Augsburg, Germany. And to remind you that I actually already sent email to you, and just to remind, your talk will be 10 minutes plus 5, okay? So 10 minutes.
Sorry, excuse me. I'm not able to share my video somehow.
Can you
my
repeat?
presentation.
Yeah, please try share screen. Can you find the share screen button? Yes, now we can see that. I actually can see your slides. Yes, that's very great. Yes, we can see that. Oh, you are also from IISER India, right?
Yeah.
So your time is 10 minutes for presentation plus 5 minutes for question and answer. So please start right now.
Okay, thank you. So I would first like to thank the organizers for giving the opportunity to present. So hi everyone, I'm Amna Ahmed, and I'm going to talk about the phase classification in disordered quantum system. This work was a part of my PhD at IISER Bhopal, and you can see this paper in which the results were published. So I'll straight away go to the introduction of my talk. In general, when we have periodic tight binding lattice and when we introduce on-site disorder to it, then Anderson localization is observed. In particular, if you have a random type of disorder, then you can observe that all the states are localized in 1 dimension and 2 dimension. So an example of a localized state would be the one on the right side. And in 3 dimension, a delocalization to localization phase transition is observed. So you could consider a delocalized or an extended state to be the one example that's on the left. However, there is also a probability to observe it in 1D if you choose the disorder to be quasi-periodic. So I'll then come to the models that we have considered in our work. The first one was a long-range Harper model. So basically, this is the tight binding Hamiltonian, where we have a long-range hopping term, and this R. So there you could consider a number of sites in which so there's a 1D lattice, but there is hopping between all the sites, and the R gives you the geometric distance between any two sites, and this is the quasi-periodic on-site disorder with the strength lambda. So in principle, here the main feature is shown by this parameter sigma, which is when it's less than 1, the hopping would be less, and hence you would observe multifractal and delocalized eigenstates. But then if this parameter sigma is greater than 1, then you could observe localized and delocalized states. And in general, if you take this parameter sigma to be infinity, then you will reach to this very famous Aubrey-Andre Harper model, which has just the nearest neighbor hopping and a quasi-periodic disorder. So, and the type of state depends upon the strength of the disorder. So if it's less than 1, you'll find all the states are delocalized, and greater than 2, it will you find all the states are localized. But at a critical strength, you will find that the states are multifractal. I'll also discuss about another model, which is actually a 3-dimensional model, and specifically because of the factor that there is a random on-site disorder there, which strength is delta. So in particular, we chose it to be between half and minus half with a critical strength, separating the delocalized and the localized states. So now I'll discuss how we the labeling. The labeling here of the data set is done with a physics quantity that's very relevant to the in condensed matter physics, and that's the fractal dimension, which you can it's actually associated with the qth moment of the eigenvector. And in the thermodynamic limit, that when n tends to infinity, it's actually 0 for a localized state, and it's between 0 and 1 for a multifractal state, and approximately it's near to 1 for a delocalized state. So this is a very good quantity that you could use to label eigenstates. And in general, you could also use any quantity, and this was the one which we preferred. So coming to the machine learning algorithm, one of the things that we did was this multi-class classification. So we chose for different values of sigma and lambda. We generated a lot of data. So that was like 3 lakh eigenstates per class, and then we calculated the fractal dimension D2 here and labeled the states as localized, multifractal, and delocalized using it. And on the right side, you can see the neural network. So we had several hidden layers here, and the input was the eigenvector amplitude. And since that could lie between -1 and +1, we chose the activation function to be leaky ReLU. And to prevent overfitting, there were several dropout layers as well. And ultimately, the goal was to get the probability of these 3 classes. So the output will have 3 neurons with a softmax activation function. So we trained 2 neural networks, one using the eigenstates of the LRH model and the other with the AH model. And in both cases, we brought the loss to 0 and accuracy to 1 without any overfitting or underfitting. And these are the results of our work. So let me just tell you, epsilon is the fractional eigenstate index. So the eigenstate index that's divided by the total number of it. And on the y-axis, you will see the disorder strength. So we have 2 cases, as I said. So the plots on the leftmost side are the plots that are very conventional to our work. That is the plot where we see the phase diagram using the multifractal dimension. So here for sigma less than 1, we see this delocalized and multifractal states. And then with the neural network that was trained on the eigenstates of the LRH model and the AH model, we plotted these phase diagrams. So let me tell you that the red color is the probability of the state to be delocalized, that the machine learning probability. Orange is for it to be a multifractal type of, and then purple is for a localized. So you can see that this has good correspondence with that of the plot phase diagram with D2. Similarly, in the case where we have delocalized and localized states, we plotted the phase diagrams, and again we found that there was a good they look with good agreement with the one that people usually measure. And also to tell you, this is from a single disorder realization, the machine learning results. So I think that's an added benefit here. And then let me come to the AH case where we had the delocalized states separated from the localized states with a multifractal at a critical point. And here also, when we used the machine learning predictions were actually pretty close to that obtained from D2. So next, I'll discuss the binary classifier. In the binary classifier, we actually had, as I said, that the AH model has separated delocalized and localized phase. So just we took 2 points, and we knew already what the label would be. So we just chose 50,000 states from each class. So we have 2 classes. And then we have this binary classifier, which has an input layer. But here we fed the probability densities here. And since that would be between 0 and 1, we simply use the ReLU activation function and got the probability P, which is of a state to be localized. So then if it's 0, it would mean that the state is delocalized. Then these are the results of the binary classifier. So here for the AH model, as you can see so above you can see all the plots are from the conventional multifractal dimension that I have mentioned before. And below we have this from the machine learning predictions. So in the AH model, you can see that the binary classifier gives very good results. You could see the delocalized states separated from the localized states. Then the second question was, what would happen to a phase that the machine learning algorithm never have seen before? Since this classifier was trained only on the delocalized and localized states, and here this light blue color is the multifractal phase. So you could see that there's some confusion in that phase with values that are neither 1 nor 0. So in fact, this is another interesting finding, that you could use a binary classifier or to find a phase that for which you have not trained. So it's an unknown phase. And another thing that we observed was, so for the AH model, as I mentioned, it's a 1D chain with n number of sites. So we trained the system with our machine learning network there. And then instead we have this 3D Anderson model, which is a 3D dimension model. and it has L cube sites. So the total number of sites in that sense would become equal to the AN. And then for a network that was trained on this 1D chain, we made the prediction for a 3D Anderson model. So this system has this is from D2 and the above plot, and then you could see the critical point is around 16. So the machine learning algorithm was able to predict this transition as well. So in a different geometry also, the binary classifier gave a good result. So to conclude, I would just say that the multi-classifier, just using the eigenstate probability, helped us to classify the different classes well. And the binary classifier, which was just trained on 2 classes, gave confusion in a third phase, which has not shown before. And so, in fact, this is a very interesting study, and hopefully we could extend it further. So, thank you for your attention.
Thank you very much, Dr. Amna. Very nice talk. And we immediately go to the question from some participants here. First, from Dr. Colin Benjamin, he asked, what do you mean by train on LRH or AAH? Does it not mean basically adding this order to LRH or AAH?
Okay. So, so let me tell you that there is a key difference. So we have these 2 models. From the broad perspective, you would say there is this quasi-periodic disorder. But then when you look at it, this LRH model, the phase diagram of it, has a lot of multifractal states, which is different from the AH model. And also when you look at the localized states for this LRH model, it's a long-range hopping model. And in a long-range hopping model, the eigenstates are algebraically localized, unlike this AH model, which had exponentially localized state. So there is a key difference between these models. It's from the physics point of view. So that's why we chose different models, trained on them, and try to see the prediction.
Right. Okay, thank you for the answer. And the next question from Dr. Gustavo. Dr. Amna, have you seen the applications in localization problems such as this in the recent Kolmogorov-Arnold networks paper? It seems to be a really interesting and interpretable approach to the problem.
In whose paper?
Kolmogorov-Arnold networks, KAN. It's recently a very famous approach.
Oh,
KAN, Kolmogorov-Arnold networks. So did you see any applications in localization problems, such as ones that you explained in your presentation?
I'm not sure about it, but in different models, yes, the supervised learning is a very, I would say it's an easier approach as compared to the others. So maybe, but I'm not sure. I've not seen it.
Right. Yeah, no problem. Maybe you can discuss also later through the Discord server. And the next question is, wait. Why are there 3 neurons in the output? Is this question for Dr. Amna? It seems yes. Why are there 3 neurons in the output of your,
Yeah, because the thing is that we have trained for 3 classes. So so then the network will give us the when once it's trained and when it's tested on states that it has not seen before. So we want to find what is the probability for an unknown state to exist in one of the 3 classes. So for that, it should give us 3 probabilities, the sum of which should be equal to 1. However, there are other approaches as well where the sum need not be 1, but this is what the one we have chosen.
Okay. And the next question is from Sahu. When you got the 3rd phase, did you extend your binary classification problem to use softmax regression?
I haven't, but it's interesting. Surely I can try it later. Thank you.
Right. Okay. Then from Mr. Jai Kaushik, he asks, as you mentioned in the presentation, that the neural network trained on the eigenstates of the AAH model exhibits some discrepancies in identifying multifractal and delocalized states when applied to the LRH model. So could you elaborate on the specific reasons behind these discrepancies?
I won't say there's discrepancy in that sense, because when we the system, when it was trained on LRH and predicted on AH, okay, I understand where it's coming from. This is actually a very small system size, like 500, on which we trained and tested. So apparently going to a larger system size will decrease it. So it's finite size effect, if that's what you're asking.
All right, and he follow up actually, are they primarily due to the differences in the nature of eigenstates between the two models, or are there limitations in the neural network architecture or training process that contribute to the discrepancy?
Where in general, if you are getting this loss and accuracy, or getting a zero loss, so that means it's the machine learning network is getting trained well. So that is not the problem of the ML network, but it might be because of the type of data that you are feeding it. In my experience, most of the time it's the quality of data, the amount of data, or what you are teaching it.
Okay.
Yeah.
So maybe I will read two remaining questions because the time limitations. Among the three models, which one is the best for face disorder classifications from your point of view?
I wouldn't say there is a best among them. The main aim that was to see, like, you have different models which have different type of localization, different type of disorder. In general, the aim is always to have a very generic machine learning algorithm that you apply on, and you train it, but then you get the result for anything that you apply on. So I wouldn't say a good result. I think most of the results were consistent and similar.
Okay. And maybe last one. Sorry if I don't read all the questions. From Dr. Doni, he said, I think the practical use of machine learning would be including many-body interaction. So how can this method be generalized to many-body system?
Yeah, sure. Then this is like for a single particle state, but then you have to go to the many-body system, and in many-body system, obviously it's very interesting to try there. And basically, there is a very key difference. Now, when you have a many-body state, you have this localizes, like many-body localization, which is similar to the many-body critical phase, because they both are non-ergodic phase. So in that sense, you will have to think a bit more in terms of the state that you get there. In terms, that's like a different problem. It won't be exactly the same.
All right. So thank you very much for the discussion session. And yeah, I just would like to remind you also once again that we have a Discord server here. Can you see my screen, Dr. Amna?
Yeah, I can.
Yes, then I will mention your name. I hope it's correct. Yeah. It belongs to your name. So then for all other participants, if you would like to ask further questions, and also for the ones who already asked in the Zoom, but I still did not read the questions, please repeat your questions here. You can discuss with Dr. Amna in the contributed one channel. Okay, so time is already up, unfortunately. So let's give applause to Dr. Amna Ahmed. And from now, we will have a medium size break for about 50 minutes. Actually, it's allocated to be 1 hour, but yeah, there are a lot of questions, so we lost 10 minutes. It's still okay. We will have break until in the CET, Central European Time, it's until 1 p.m. So we will start again in 1 p.m. Okay, 1 p.m. CET. So please convert your time zone accordingly, following the ICTP website. And yeah, we will stop the recording for this session so that the organizer can later download and upload to the ICTP website. Okay, so yeah, that's correct. So then thank you for your participations in the morning session, okay, in Central European Time of this workshop. So see you again at 1 p.m. with another moderator which will be Dr. Rafika for the contributed talk number 2 and number 3. So for second contributed speakers and third contributed speakers, please prepare yourself, and we will see you from 1 p.m. So thank you very much. We will just take a break for now until 1 p.m. So see you again at 1 p.m. Bye.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium, merah pipinya. Kampungan jauh di mata, kunwangsan sebaku lilian, takkan aja kawan-kawan lamu, sangke basuh yang sulia.
Indonesia dengan ini menyatakan kemerdekaan Indonesia. Hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru gunungnya Bamega Bamanaku di Samangkarang Bamanaku di Samangkarang Tatamu lawanlah Adinda iman di dadaran Samalayang iman di dadaran Samalayang sayang si patokaan matego gorokan sayang si patokaan matego gorokan sayang sajojo yumadam ko bisa papare samuna muna keke samuna muna keke soleram anak yang manis janganlah dicium sayang kalau dicium merah pipinya kampuan jauh di mato kunwangsan saya berkuliliang takkan aja kawan-kawanan lamo sangke basuh yang surya.
Indonesia dengan ini menyatakan kemerdekaan Indonesia hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With a million timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru gunungnya bermegah, bermegah, bermanapun di Samangkara, bermanapun di Samangkara. Bertemu lawanlah Adinda, Adinda iman di dada rasa Malaya, iman di dada rasa Malaya. Sayang, sayang, si patokaan matego, tego, gorokan. Sayang, 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 si patokaan matego, tego, gorokan. Sayang, sajojo, sajojo. Yung madam ko bisa berparis samuna muna muna keke, samuna muna muna keke. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium, merah pipinya. Kampunan jauh di Batu, Kunwang San saya berkuliah, takkan aja kawan-kawan nalamu, sangke basuh yang surya.
Indonesia dengan ini menyatakan kemerdekaan Indonesia yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With 1,000,000 timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru gunungnya bermegah, bermegah, bermanapun di Samangkaram, bermanapun di Samangkaram. Bertemu lawanlah Adinda, Adinda iman di dadara, Samalayang iman di dadara, Samalayang. Sayang, sayang, si patokaan, matego, tego, gorokan. Sayang, 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 si patokaan, matego, tego, gorokan. Sayang, sajojo, sajojo. Yumanam ko bisa berparis samuna muna muna keke, samuna muna muna keke. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium, merah pipinya. Kampuanan jauh di Batu, Kunwangsan saya berkuliah, takkan aja kawan-kawan alamu, sangke basuh yang suria. Tak lelo, 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 ledo, sak menang, ojo pijer nangis, anakku sing ayu rupane, tetiap pandekare bangsa.
Proklamasi kami bangsa Indonesia dengan ini menyatakan kemerdekaan Indonesia hal-hal yang mengenai pemindahan kekuasaan dan lain-lain diselenggarakan dengan cara yang sama dan dalam tempo yang sesingkat-singkatnya. Jakarta, 17 Agustus 1945, atas nama bangsa Indonesia, Soekarno, Hatta.
Indonesia is the most beautiful land in the universe. The land where we were born. The nation where we grew up. So many colors that live together in peace. With 1,000,000 timeless treasures. With an abundance of natural wealth. Indonesia is not just wonderful. Indonesia is a wonderland.
Kota baru dunia bermegah, bermegah, mana di Samangkaram, mana di Samangkaram. Katamu lawanlah Adinda, Adinda iman di dadara, Samalayang iman di dadara, Samalayang. Sayang, sayang, sifat toka amat tego gorokan. Sayang, 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 sifat toka amat tego gorokan. Sayang, sajojo, sajojo. Yumanam komi sabapare samuna muna keke, samuna muna keke. Soleram, 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 anak yang manis, janganlah dicium, sayang kalau dicium, merah pipinya. Kampuangan jauh di mata, kunwangsan sebaku liliang, takkan aja kawan-kawanan lamu, sangke basuh yang suliang. Tak lelo, 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 ledo, sak mana poco pijar nangis, anakku sing ayu rupane, tetiap pandekare bangsa.
Indonesia dengan
Tribute Tech Talk Session. I'm Rafika Rahmawati from National Research and Innovation Agency of Indonesia, and I'll be the moderator for this contributed talk session. Same as the previous session, each speaker have 15 minutes, 10 minutes for presentation and 5 minutes for discussion. Before we begin, I would like to introduce you the second speaker. The second speaker is Dr. Said Abedi. Hello, Dr. Said Abedi.
Hello, can you hear me?
Yes, I can hear you. Are you ready for the presentation?
Yes,
Could
I'm
you
ready.
start the share screen?
Okay, let me share my screen.
Yes. Dr. Said Abedi comes from Department of Physics, Isfahan University of Technology, Iran. He will present his topic about materials future library Python package. Okay, without further ado, I'd like to welcome our speaker to start the presentation by now. Your time is 10 minutes, Mr. Said Abedi.
Thank you very much. My name is Said Abedi. I'm a PhD student in condensed matter physics at Quantum Simulation of Materials Laboratory at Isfahan University of Technology. We thank the workshop organizers to accept our abstract for online presentation. I want to talk about our materials feature library package that in short we have called it MATFLib. Okay, in general, machine learning approaches in material science have three main parts. One of them is materials databases. Another one is material representations. These representations transform materials data into a proper numerical feature space that can be used for machine learning algorithms. These representations are a set of parameters that capture the underlying mechanism of a material property. The last part is machine learning algorithms that use to train and then do prediction for new materials. Material representations can be categorized into three different types. The first one is elemental and compositional features. These features relate to constituent element of compounds. Examples are atomic radius, Mendeleev number, ionic character, and so on. The next type is bulk features. These features can be obtained from DFT calculations. For example, for the formation energy, bulk modulus, and cell volume. The next type is structural properties. These features relate to atomic positions in crystals. A smooth overlap of atomic position and many-body tensor representation are of this type. The present and initial purpose of the MATFLib package is to implement functions for preparing elemental and compositional features. The package publicly available from the GitHub. Its address is shown here. This tree diagram also shows the structure of the package. Currently, MATFLib has 3 branches. The atomic features branch contains a script for obtaining elemental and statistical features. The data branch contains atomic feature sets or collections. And the plot branch contains scripts for plotting the periodic table of elements. The package is licensed under Apache license. In MATFLib, we are focused on simplicity and user-friendly of the package. There are some useful functions like available collections and available features to prepare information about available collections in the package. The fetch elemental features and fetch statistical features are two main functions of the package, and in the following I describe them. We also working on compositional and structural features. We prepared the Matplotlib documentation in the form of a standard Python package documentations, and it is available online. Okay, let's talk about functions more technically. The available collections return a data frame that have information about collection names and their descriptions. The available features function also prepare feature names of a given feature collection. The fetch elemental features get the user materials data as input and return a data frame that its column have atomic features. It has three arguments. The first one is the data. This argument can be in the form of a single string, a list of multiple materials, or a pandas data frame. The next argument is feature collection. Users can select one of the available collection from the package, or even they can use their own feature sets. The next argument is feature name. Here, the default value is all. In this situation, the function return all available features within a collection, but it can be in the form of a single string or list of multiple feature name. The Matplotlib contains DFT calculated and package-specific feature collections. We obtained DFT calculated features in collaboration with Professor Matthias Scheffler and Dr. Lukas Fupa at Fritz Haber Institute. These features calculated using the FHI-EMS package and by different DFT approximations. The package-specific feature collections contain collected data from the Mendeley, the PyMatGen, and MatMiner packages. Another important function is fetch statistical features. This function is useful for databases that have a different number of atoms in their composition. This function returns a data frame that have a statistical measure of atomic features. The first three argument is similar to before. There are a new argument for a statistical measure of atomic features. Here also the default value is all, but the user can select a single or list of supported functions. The supported functions are shown in this box. The package also contains a periodic table function that is useful for plotting the periodic table heat map of a selected feature. Okay, at the end, I thank QSM Lab faculty members, Professor Akbarzadeh, who is the head of the group, my supervisor, Professor Hashemi Fak. I thanks Professor Alai and Professor Abdul Husseini. I also thanks my colleague, Mrs. Samira Bani Najarian. She is a PhD student, and we both are working on the Matplotlib package. Thanks for your attention.
Thank you for the brief presentation, Mr. Said Abedi. And then this is a time to discussion. the audience can raise hand and type the chat from the Zoom chat. This is one question from Chen. I will read it. From where can we data of materials for use in Matplotlib for exercise?
Okay. For exercise, you can see here one example that I run the code. As you can see, the fetch elemental features get a single string and the output in the form of a pandas data frame.
Any
I can't hear you.
Any question again from the audience? Oh, this is how can I install Matplotlib? Can I find it using page, for example?
Okay, the Matplotlib available from GitHub, but we are trying to complete a workflow to publish the package in PI website. We try do this as soon as possible, and then you can install it using the PIP. I can also provide the binary of the package if everyone contacts me.
Thank you. And then can this package be used to calculate band gap energy and density of state?
No. We just use the available features from some sources. We have DFT we just use atomic features, not features for compounds. We use the atomic features for preparing for materials.
Okay, this is from Sunil Karki. Why are you using Matplotlib?
The Matplotlib is a package for preparing the data for machine learning algorithms. It can be simplify the way from materials to machine learning algorithms.
Okay, there is the more question again. This software program is DFT or predicting the properties of materials from Srinivasan.
Can you repeat that again?
The software program is DFT or predicting the properties of materials.
No, it's not a DFT program. It is a package for preparing atomic features for compounds. We can use it to transform material composition into a proper feature space that can be used for machine learning algorithms.
And this is Angga Dito Fauzi want you to take to put the download link of Matplotlib in the chat book.
Okay, I put it. Yes, okay.
Okay, this is the next question. Does this package create new materials? What is the use of it?
No, it's don't create new materials. You can prepare a list of materials, and the package get it as input, and then prepare atomic features or compositional features for it. You can see the example in this image. For example, Al2O3 have chemical symbol Al, atomic number 13, and atomic energy HOMO FOMO Al, that is a small number. It creates a feature space for using in machine learning algorithms.
Okay, thank you. I think this is a last question. If you think this is not enough, we can continue this discussion in Discord channel. Thank you, Dr. Said Abedi, for the great presentation and discussion. I will please to operator to stop the recording.
Thank you very much.
Thank you, Mr. Said. Okay, now we will listen to the next speaker. Before that, please operator to start recording. Okay, the next contributor talk will be presented by Dr. Colin Benjamin. Hello, Dr. Colin Benjamin. Are you ready for the presentation?
Yeah, I'm ready.
Doctor, yes, thank you. Could you start to share your screen first? Okay, Doctor. Yes, Dr. Colin Benjamin comes from School of Physical Science, National Institute of Science Education and Research, Bhubaneswar, India. In this session, he will explain his work about resolving degeneracies in Google search via quantum stochastic walls. Same as before, the duration is 10 minutes for presentation and will be continued by discussion. Without further ado, I'd like to welcome Mr. Benjamin to start the presentation by now.
Sure. So this work is based on this paper, which you can find here. And I work in NICER in India. So let's start with what is a quantum walk. So we know about classical random walks where we toss a coin and go either to the left or right on a 1D line, and we get a Gaussian probability distribution. If you do it many times, you'll see. What is a quantum walk? Where we have a quantum coin, which can be any unitary, basically, a quantum unitary. And because of that, we get different probabilities of getting, this probability distribution, if you plot, is no longer a Gaussian, but it is skewed either to the left or right, depending upon the initial state of the coin. But the real advantage of quantum walk over a classical walk is that it spreads much faster. So if we use it in some algorithm or in some other purpose, we will get multiple advantages of this spreading. If you have a superposed initial state, you will get a symmetric distribution, probability distribution. In contrast to discrete time quantum walk, which I showed you before, a continuous time quantum walk involves the unitary evolution of the whole Hamiltonian. So if you have a 1D line with some probability of jumping to the left or right and with some probability of staying there, basically you will again get a probability distribution which is symmetric across in a 1D line, and given a certain factor, which is the probability of jumping from one to another, you can get
Dr.
back.
Colin, I'm sorry. Can you change the slide because it's entire slide here.
Sorry, what's the problem? No, this is the entire slide. Yes.
You can swap display.
You can swap the display in the top of the screen.
Okay. So you cannot see my screen? What's the problem? I don't get it.
Yeah. Now you are in presenter view mode. Can you?
I don't have to show my entire screen. I don't.
Okay. Okay, it's okay. Can you make it yes? Can you make it full screen because this is to slide here to screen.
Oh yeah,
I'm so sorry.
Screen. On my computer, it is full screen.
Oh. Yes.
Yeah,
okay.
Now it's better.
Okay. Yes. Start to.
Okay, I was here.
It's not full screen again.
Yeah, and this is a continuous time quantum walk, which reproduces what we got in a discrete time quantum walk. But my main purpose here is what is Google PageRank and how we resolve degeneracies better. But there are some applications of quantum walks on universal quantum computation, quantum search algorithms, as I will discuss later, PageRank algorithm, single particle entanglement. We have written some work on that, transport and energy transfer in photosynthesis, and we use quantum walks to model these systems. So let's go to what is quantum PageRank and how we improve upon classical PageRank. So classical PageRank, as you know, was devised by these two chaps, Sergey Brin and Larry Page, long back. And my outline is as follows. First, I will discuss what is classical PageRank and its relation to continuous time random walks. Then I will discuss what is a quantum stochastic walk. Then I will discuss what is quantum PageRank with two distinct models of quantum stochastic walks, one which uses only incoherence and the other which uses dephasing and incoherence. And then we will look at different networks like spatial scale-free networks, Edders, Renyi, Watts, Strogatz, to model quantum stochastic walks and to implement Google PageRank on them. So what is the PageRank algorithm? So PageRank algorithm ranks web pages. When we go to Google search engine and we type in a search, we get output which ranks the search string from the most relevant to the least relevant. So in descending order, it ranks. And that was the great advantage of Google PageRank actually. So what determines what goes on top of that list and what goes at the back? Well, the number of links that web page has to others determines the links, as well as what's the quality of that link. That is how many links go back to that website, say. So here I mean, when I look at a link is a link between two nodes. A node is like a website, a web page, whatever, and any transfer of information from one to another website is a link. So even if our website has few links, if the links are from very well-known website, then it is likely to receive a higher rank. So this was the idea of the Google PageRank, and you can learn more about it in this paper. What are the main features of Google PageRank? Complexity. The first is the World Wide Web is vastly complex network involving many websites and associated links. So to rank web pages in such a network is extremely tricky, and to distinguish between the importance of one website vis-a-vis another website is very difficult. And many times classical PageRank gives the same weightage to both websites. And in that situation, it's very difficult to distinguish for the user which website to go to. So what I mean is, if there are degeneracies in the rank of several websites, then it lowers the search quality. So basically, let's start with looking at what Google PageRank exactly is. So there are two parameters, as I said, which define the efficiency of the Google PageRank. One is the degeneracy. That is, if two websites get the same rank, then there's a degeneracy in the ranks, and we don't want that to happen. And second, of course, is what's the speed of your search algorithm. The better algorithm has to return the least degeneracy, and that one has to also converge very fast to the result. Now, as I said before, Google PageRank is a two-step process. Based on your search query, a list of websites with matching content is listed in no particular order. And most pre-Google search engines, for example, when I was a PhD student in the beginning, we used to go to Lycos, LookSmart and all, and they have entirely vanished when Google came along. So the user looked through a list and found what was helpful, and generally he or she scrolled down sequentially. So Google's masterstroke was to add a second step, was to rank the website with the matching content based on the links, as I discussed before. So to do this, what it did was it implemented the search engine on a continuous time random walk. So what is it? The website with the highest rank on this network came up on top, while the least connected network came at the bottom. So how do we implement it? You first write an adjacency matrix for a network of web pages. So adjacency matrix will have weightage 1 if the wedge is directed from say J to I, and 0 if it is undirected. If it is undirected, then both will have weightage 1. And similarly, you write a Hamiltonian or the adjacency matrix where DJ is the degree and gamma is some weight factor which you give, and you try to iterate it continuously to find the probability. You start with some probability distribution, say P0, you start at some initial site, initial web page, and then you iterate it simultaneously, and you, at the end of this large scale iteration, you will reach an equilibrium, and that equilibrium is the entries of that probability, which give you the probability of the ranks, and they will automatically rank your web pages in the order in which the highest connected web page comes out on top. So this is the basic algorithm for the Google PageRank. Now, to implement it, you have to give some weights. You give the weight if the websites are connected, A, and there's this alpha factor, where alpha depends on what is called the damping factor, and it controls the ratio of the random jumps from one edge of the graph to another graph or network. So what is quantum stochastic walk? It's basically from the continuous time quantum walk, you go to a quantum stochastic walk where you add decoherence to your quantum walk. The way to add decoherence is by these factors. I will explain them a little bit later, by using what is called the Kosowski-Lindblad master equation. So you start with a weight factor W, which represents the interaction of your quantum walk to the environment, and depending upon that weight, you will have different kinds of models for the continuous time stochastic walk. Since time is limited, you can learn about quantum stochastic walks in these papers. And basically what stochastic walk means is it is a quantum machine learning approach. What is machine learning? Basically, it is adding stochasticity to your problem and then doing a statistical analysis of that. And that is what we'll be doing here. So there are two models which we'll implement. One is where we have only incoherence. That is, only the off-diagonal elements of your Google matrix, which I described, will be affected. And another which is dephasing and incoherence, that both the diagonal and off-diagonal elements of your Google matrix will be affected. So when you start, you again do the same thing as I was saying of a quantum classical time random walk, but now use the Lindblad equation, which is the quantum stochastic walk. You start with some initial probability distribution, and then you iterate continuously this equation. This Lindblad
I'm sorry,
equation.
Mr. Colin, your time is 1 minute remaining.
Okay, till you reach equilibrium. And that equilibrium we'll find has much less degeneracy than the classical PageRank algorithm. So we do two calculations. One is what is the degeneracy, that is what is the weight each link has, and then how fast our quantum walk converges to the search result. And we use 4 different types of networks. One is scale free, which has a distribution like this. Examples are Barabasi, Albert, and Price graph, Watt-Strogatz, Edosveny, and spatial networks. And all these are examples of small world networks. And what are the properties of small world networks? Any two nodes have very relatively small distance. Two, clustering is high, and hubs like bicycle, you know the spokes on the hub. So just like that, there are hubs present in those. So we'll start with the Edosveny network, and you can see the page rank. Sorry, just 1 minute. So this is a page rank for quantum page rank, and you can see the degeneracy versus how fast they converge here. So you can see in the classical page rank, there is no degeneracy. In quantum also, there is no degeneracy. And speed of convergence is almost same as classical. Now we go to Watt-Strogatz, and I will end here. You can see the degeneracy is much larger. We have 5 networks with 100 vortices for this Watt-Strogatz network. Classical page rank gives huge degeneracy of 10. Quantum page rank reduces it to 4 and 3. And then the convergence time is much faster. You can see this is the line of the classical page rank algorithm. As you change omega, you can see it ranks much faster, and I won't take much time. I will go to
I'm sorry, the time
conclusion.
is over.
Yeah. Sorry.
Yes.
So this is the conclusion, and this compares all the different networks. So thank you very much for your time.
Thank you, Dr. Colin. It's very great presentation. And now the discussion. This is from Itun Akon. I have 2 questions. One, does the domain name for different websites affect Google ranking of this site, like .org or .com and etc.? How does quantum works on different websites? Thank you.
Okay, so the first thing is the Google page rank is nothing to do with quantum or classical, works only on the content of the web pages and the links with the content. For example, if you search for some content where you write a string for say physics or something, you'll see it doesn't matter whether it is phys.net or phys.com or phys.org. If the content is relevant, then it will get a higher search. And the second question was on, oh, sorry, I forgot. What was that second question on? Sorry, means how to implement it. So we have given an example of, see, a quantum network on any network is basically a small world network. And we have given examples of Watt-Strogatz, Edosveny, scale-free, and spatial networks. So any quantum page rank can be implemented on any of these networks. So a quantum internet network is basically any of these 4 networks. It can be any of them actually, depending upon where and from what and what is your search string you are searching for.
And then the next question from Sunil Karki. Why classical page rank gives same weight but not in quantum?
So that's the basic idea. When we go to quantum is basically much more, how to put it, because of this omega factor, the degeneracy ranking, you get more, how to put it, you can resolve the degeneracies much better. Because in quantum case, you have the continuous time quantum walk has means a walker doesn't go from one to the other node via just a link which is either 1 or 0. It goes from one to the other link by a phase factor also. So the phases which you include in your continuous time quantum walk, although they are affected by the decoherence and dephasing, they still retain their some phase, and therefore they can resolve these degeneracies much better. I hope I have answered a bit of the question, because it has to do with both the quantumness features as well as the how the environment affects the continuous time quantum walk. So the phase factor which is inbuilt into the continuous time quantum walk helps in resolving the degeneracies better.
Thank you, Dr. Colin Benjamin. It's very interesting discussion, but I'm so sorry. We have the limited time. we have only 15 minutes for a contributed talk session, and we have a next session. Thank you, Dr. Colin Benjamin, for the great presentation and discussion. If you feel the discussion in this session is not enough, you can continue the discussion in the Discord channel. Okay, please operator to stop the recording. And I'm so sorry if I have mistake is in this moderator. Thank you very much.
Thank you.
Afternoon. Everyone, good afternoon. Thank you for still being with us. Let's jump to the next session, which is a keynote speaker. But before that, I will introduce myself. My name is Jumaida. I'm the member of the Research Center for Quantum Physics. Here, I will be your moderator. And next session would be delivered by Professor Khairul Anwar. Before that, I will read the brief CV. Okay. Okay. The title of keynote session is From Quantum Machine Learning for the Current 5G and Future Modulation of 6G to Condensed Metaphysics, which is will be overview of quantum machine learning for fast mapping of low-order modulation of future wireless communication beyond the 5th generation, including 6G and beyond, expecting to provide insight for quantum machine learning for condensed metaphysics. And Professor Khairul Anwar, currently his work in the University Center of Excellence for Intelligent Communication, Telkom University, Indonesia, and he received master and doctoral degrees from Graduate School of Information Science, Nara Institute of Science and Technology in 2005 and 2008 with the theme Wireless and Mobile Communication. And here, Professor Khairul Anwar is already present. Hello, Professor.
Hello.
Are you ready
Dr.
for this?
Jessica.
Hello.
Yeah.
Okay,
I hope that you
thank
hear
you.
my voice clearly. Yeah.
Yes, I can hear you clearly. So without further ado, please welcome Professor Khairul Anwar, and the time is yours.
Okay, so thank you very much, Dr. Jatmika and everybody. So please allow me to share my slide. I do hope that you can see full screen of my slide.
Yes, it's already
okay.
full
So
screen.
thank you very much. Okay, so please let me start this talk. So I have 1 hour to present this research, and I do hope that you can take some advantage from this result, and I do hope that from discussion with you we can take also a future action for the next research. Okay, so thank you everybody and welcome to this session. So I am Khairul Anwar from the University Center of Excellence for Advanced Intelligent Communication, or ICOMS, in Telkom University in Indonesia. So the title of my talk is From Quantum Machine Learning, QML, for the current 5G and future modulation of 6G to condensed matter physics. So we have at least three keywords here. So the first is the quantum machine learning. So I do hope that I can make a brief review about what kind of QML that we can apply, we can use for the condensed matter physics, I do hope. And then the second is that the modulation. The modulation is one of the important part in the current 5G and the future 6G in 2030. I put the name here future modulation because for the 6G, the standard is not decided yet. The standard may be in 2027 or 2028 of 6G. But with the development of the quantum machine learning, I do hope that we can solve many difficult problem of the future modulations. And then I do hope that for you from physics, I do hope that you can take some advantage, especially for the pattern that you can extend the scale into the larger scale, such that small circuit you can extend to solve many problem of the requiring big circuit. So those are the keyword of this talk. Okay, so this result has been presented. Some of the result has been presented in the Conquest. This is the international conference held by the BRIN in 22nd and 24 November of 2022. Okay. Okay, so before I start my talk, please allow me to introduce in 1 second about the university. So we are from Telkom University. Telkom University is #1 private university in Indonesia. And ICOMS is my research center here. So I lead this ICOM since 2016. And then currently we are also leading a new laboratory, which we call the Beyond 5.5G laboratory, where we are studying the artificial intelligence, classical artificial intelligence, and also the quantum key distribution, basically the quantum cryptography and also the quantum error correction. So I do hope that we can take some insight from the current result. Okay, so we started our lab in 2016 after my return from Japan, and in 2020 we changed the name into Advanced Intelligent Communications, and we are assessed by the government as one of the research center in Indonesia developing the intelligence for telecommunications. And we are having the, Alhamdulillah, almost good funding. So we spend almost every year about 4 billion rupiah for the research on 5G and 5.5G and also 6G, including the quantum communication, quantum error correction, and also quantum key distributions. Also the quantum machine learning. And then this is the outline of my presentation. So first, I would like to explain why we need to study about the QML for the modulation, current and future modulation. And then after that, the system model and the proposed quantum machine learning. So we review the classical square distance machine learning and also the proposed quantum machine learning, and also the some mathematical proof that some algorithm in quantum provide the same result as the classical, but with the faster computations, and then performance evaluation, and finally I will conclude this talk. And then, okay, so I will discuss the detail of this figure between classical and quantum machine learning, the difference, and also some very simple quantum circuit, but it solves a big problem that we are facing in telecommunications. And then, okay, so the next, okay, so this is there's some updates from the Mobile World Congress in Barcelona into 2023 and also 2024. So we are currently developing the 5.5G, where the artificial intelligence is the main part of the technology, and also preparing the 6G, where the AI and also the quantum algorithm will be combined to provide more secure and also fast communications. So the left-hand side, this is the equipment from the Rodi and Swart. So they invited me at the time to see the demonstration how the artificial intelligence can replace the current algorithm in telecommunications, and the results are almost the same, and even with the better and faster computation compared to the traditional way. And then at the right hand side, this is some approach to the quantum for the telecommunications. So we have here the Schrödinger equation on the floor. It is indicating that we are in telecommunication are planning and also approaching the use of the quantum technology for the application, especially for the quantum information for the telecommunications. And then this is also motivate us about the digital transformation. So we can see here that there are 3 layers of the digital transformation. So the first, this is the digitization, where we have the 2G, 3G, 4G, 5G, and 6G, and IoT will be the main technology for the first layer of this digital transformation. And in the second layer, this is the digitalization, where we have the quantum computing, blockchain, cloud computing, and also artificial intelligence, the main technology to analyze the data. And on the top of the layer, we have the digital business and operating model, because we can use the data resulted from the machine learning and with the fastest computation of the quantum, such that we can monetize the data and we earn money. So this is the dream of the digital transformations that motivate us to develop some combination of quantum and machine learning in the current technology. And then everybody here, I would like also to introduce the capabilities of 6G, which just released by the ITU. ITU is the International Telecommunication Union, which is the big organizations that regulate and also manage the telecommunications globally. And we have completed the capabilities of 6G. So we have here the 2 circles. So the left-hand side, this is what we call the capability of 6G. We have the green color. This is the enhanced capability of the IMT 2030 developed from 5G. While the blue color, this is new capabilities of the 6G, which is not existing in the current 5G. So in this requirement, in this capability, we are expecting that the quantum machine learning and also the quantum algorithm are supporting the user experience data rate and also the security and privacy here, and also the coverage and also AI related capabilities here. So this is the expectation from the future 6G to the current development of the technology. While at the right hand side, which is related to the current technology, is that we have the security, privacy, and resilience here, which is the one of the 4 pillars of the 6G, and we have the ubiquitous intelligence. While the use cases of the 6G is we have the additional 3 use cases compared to the 5G. So 5G is in the green color here: immersive communications, hyper reliable and low latency, massive communication. This is the extension of the 5G eMBB, URLLC, and MMTC. While the new capability of 6G is shown in the blue color here: integrated sensing and communication, integrated AI and communication, and ubiquitous connectivity. So this ICTP workshop are very much related to the development of AI and communication, and also for the some algorithm and computations using the machine learning for the telecommunications. And then when we are talking about where will be the position of the quantum in the mobile communications, so this is our expectations. So everybody can see that here in the 5G, we have the mobile users, we have the base station or Keynote B here, and then we have the core and we have the network. So the difference between 5G and the 5G advanced is the existence of the intelligence in the base station and also in the core. And we are also having the satellite here, where satellite can be the backbone, or the user can also direct connection connected to the satellite here. And what about the 6G? So for about the 6G, we will be having the double channel. So the black line, it is the classical channel, which we are currently we are currently using in 5G and 5G advanced. And then the dotted line, it will be the quantum channel we are using to distribute the key, especially for the quantum key distributions. So we are having the connection between the base station and the core, and also the core and the networks, where for covering very long distance, we need the satellite help to distribute the quantum key. So this is the possible implementation of the quantum and also the quantum machine learning in the telecommunication. For the machine learning, I do hope that the implementation will be more in the base station and also in the core, rather than in the satellite, because of the limited processing and also the limited power of the satellite. And then this is also, I would like to invite also everybody who are living in the ASEAN countries, that every year we are having the call for proposal. So we are trying to submit this proposal in September 2024. So we still have enough time. And completed proposal should be in December 2024 or the early of January 2025. So I think that we can make collaborations to develop the future technologies for telecommunication, and also maybe some insight from the condensed matter physics. And then, okay, so I want to go forward to the main talk of the today's session. So this is the system model, everybody. So the system in this slide, I would like to show the simple description of the telecommunication, where, for example, this is the transmitter. So the transmitter, we have the binary information B, we have the modulation M, and we have the symbol X here. And then we have the antenna, and then we transmit. When we are considering the broadband communication, and then we have the many paths here. And then at the receiver, our signal are received by the antenna, and then corrupted by the noise, and then we should modulate, and then we return back the information to the P head here. And then for the model of this transmission, we have a Y equal to the matrix H circulant X plus N. And then, however, the problem is that in telecommunications, we have to transmit the signal not in the form of the binary, but in the form of the symbol. So the symbol is expressed, for example, if the bit is 0, and then we use 1 by square root 2 plus j. J is the imaginary part of 1 by square root 2. So this is to represent bit 0, and this is to represent bit 1. So what we transmit between transmitter and receiver is this symbol. And then the problem is coming from the fact that if the user want to transmit more bit, then we need more symbols. And then when at the receiver, the number of symbol, when the number is very large, and then it is difficult for the receiver. So we are expecting to use the quantum machine learning instead of the classical machine learning here to solve this parallelly. So we can exploit the parallel processing, the natural parallel processing of the quantum machine learning to solve the problem of mapping this symbol into the binary. So this is actually the main problem that we are trying to study in the sessions. And then before we are going to the detail of the modulation, so I do hope that we understand the philosophy, the small philosophy of how we can increase the capacity. Of course, the capacity cannot be increased. Capacity is depending on the channel. I mean, how we can have the communication with high capacity. So let's, this is the general equations that currently still working even for 5G and also the 6G. So the target of the 6G is 1 terabit per second, which is expressed by C. And then K is, this is actually the new constant that we are trying to find. For example, it can be implemented using orbital angular momentum. That's why this is also very big connection with the quantum, and also using qubit, for example, not only qubit, but qubit. So maybe with those technology, we can have the additional constant here. N is the massive MIMO. This is depending on the number of antenna you are using. And B is the bandwidth. And then this is logarithm basis 2. And 1 plus M is modulation. And R is error correction. And H is the channel. And N0 is the noise, spectral density. And this is the energy. And then this is the unit. So currently we are working on the M here. Of course, if you are trying to say that if we increase the number of M, it does not increase the C linearly because of this is the logarithm function. However, yeah, for the 5G, we are using 124 QM currently. And then for the Wi-Fi 7, yeah, if you are hearing the news about Wi-Fi 7 and also Wi-Fi 8, they are trying to use even bigger than 1024. I hear that they are using 2048 dot here, which is very difficult and very sensitive at the receiver. When you are trying to decode, you have to check to every positions. So when the number of the symbol here are increasing, and then the complexity is increasing exponentially. So we are expecting that the development of the quantum machine learning will be helping a lot for this telecommunications. And then after we are knowing about the philosophy of the capacity and the modulation, now I would like to highlight here the modulation is just before the antenna, and we have the Shannon bound here, Shannon bound, Shannon limit, where the left-hand side, this is unachievable region. So this is impossible for the human to reach this area because the y-axis is representing the spectral efficiency, and the x-axis, it is representing the EBN0 or energy bit per noise. So what the people are trying to do is to have the telecommunications that works in this area close to the Shannon bound. And then the modulation is used to increase the spectral efficiency such that we can touch the Shannon bound. Of course, not exactly touch, but close, close to the Shannon bound. So when we are having equipment that have the performance close to the Shannon bound, and then it is said that our technology is very efficient because it is very close to the Shannon bound. It means that we can utilize the power, utilize the spectrum with less power, but transmit more information. And then the relation with the condensed matter physics, maybe, this is my guess and also my expectation that still we have the relationship with the condensed matter physics is that in the modulations, for example, we have the 4QM, we have 4 dot here. And if we have the 16QM, we have the 16. If we have 64QM, we have the 64 dot here. So with this structure, actually the design of the quantum circuit for the quantum machine learning is not so difficult. You can just make a copy, but of course not just simple copy, but with the clever design of the copy, because some structure maybe not work linearly, but maybe we need to modify the position of bit to have this, to have the good detection, to have the good performance at the receiver. So basically like this. So I do hope that with this phenomena, we can take some insights from telecommunication to the condensed matter physics. Okay, let's take an example of the 5G modulation using 256 QM. So in the standard of the 3GPP, this is decided that the mapping from the binary to symbol is following these equations. So for example, if you have 0, 1, 1, 0, 1, 1, 0, 1, and then your symbol is this position, it means that 13 plus 13 minus J divided by square root 170. So this is the symbol for the 256 QM. So the difficulty is coming from how you detect 0, 1, 1, 0, 1, 1, 0, 1 like this. If you receive the symbol not exactly its position, so you have to check one by one. Yeah, and then the current modulation is that this is with the square pattern like this because it is very easy and very practical. But the Shannon said that this is actually not good. Yeah, this is actually not good. So if in the future with the capability of machine learning, if somebody can design more random modulations, that's the efficiency will be very good. But usually the random modulation is difficult. So we are trying to exploit the quantum machine learning. Maybe we can design such kind of the dream random modulation in the future. And okay, so I do hope that you can take the message already. And then now let's work on the more technical. Yeah, more technical on how we can use the machine learning and how the quantum machine learning work very beautiful to help us to make the mapper. So equation number 3, this is the classical mapper to obtain the log likelihood ratio, which is defined as the logarithm of the probability bit equal to 0 given the received signal y, and probability of bit equal to 1 given the received signal y. And then from this equation we can extend. Yeah, we can make the detailed expression from this using this one. And then based on this, yeah, I think from this point, and then we can decide. Yeah, we can expect the symbol. This is the transmit symbol, and H is the channel and Y is the receive signal. Then we can decide from L here either the bit is 0 or 1. If the L equal to positive value, and then bit is being 0, and then if L is negative, and then bit is being 1. So this is the target. And then by some mathematical modification or manipulation, we can obtain number 4, equation number 4 here. And then from number 4, finally, we can obtain probability of bit equal to 0 given Y is equal to this, while probability of bit equal to 1 given received signal Y is equal to this. Yeah, so the difference, this is almost the same equation, the same, but the difference is the number of the bit here. So given modulation with bit 0, this is you should sum all possible x having b equal to 0, while in this case we have to sum all possible x having bit equal to 1. So if you can do this, classically you have to check one by one. For example, the received signal 1, you check to x1, to x2, to x3, x2, x4 until 2048. So basically, in the traditional way, you should do that. But with the quantum machine learning, we are expecting that we can avoid such kind of the one by one checking. So in this presentation, we recognize that we are having at least 4 encoding. So the first here is amplitude encoding. We have alpha 0, alpha 1, alpha 2, alpha 3 from the cat psi here. And then we can also use the basis encoding and also Hamiltonian encoding and also time evolution encoding. But in this presentation and what we are currently doing is we are using the amplitude encoding because this is according to my experience, to our experience, that it is much simpler and faster compared to other encoding. However, everybody, if you have better knowledge about the other encoding and also better idea, so we are welcome to another development of the quantum machine learning with this encoding. And then based on the amplitude encoding, so first for the proposed quantum machine learning, this is okay. So I should say that this circuit, this very simple circuit, it is used to map the complex PPSK of the 5G. So in the 5G, we have the strange modulation like this. Usually, when somebody use a BPSK, this is and in this position, and one is in this position. But in the 5G, we have the strange position like this. But it doesn't matter actually. The quantum machine learning will solve this one. So we have the 4 qubit here, and for the step 1, we use the amplitude encoding. So we have the training here. The training is the standard modulation. Yeah, it is decided by the 3GPP. So everybody can just use the standard of the 3GPP to put in the training here. While the data here is the training of our machine learning here. And then step 2, we put the Hadamard here. And step 3, we put the measurement for the qubit number 1. And then step 4, this is actually the result to obtain the bit is actually 0 or 1. So this is really very simple, and for us it is very surprising that the machine learning, quantum machine learning, help us a lot that disrupt the traditional mapping into this quantum machine learning. So this is our mathematical proof. So X is the received signal. Let's say that here, because this is the complex symbol, we have the A divided by square root 2 plus J divided by square root 2, and then this is the received signal. And then from the power, the power, and also the principle of this is still classical, no quantum here. Yeah, from the principle of telecommunication, we have the A square plus C square equal to 2, because this is power of the A and C here, and because we put the square root 2 here, and then this also plus 2 equal to 2, and then we have the equation number 11 here. Equation number 11 is the probability of B. Yeah, this is we are trying to modify, to manipulate this mathematics such that we can use the quantum machine learning work like this. And then to make faster computation using quantum computer possible, we need to modify the equation number 11 here. So this is to obtain the B. Yeah, we modify into this. So everybody can check. I can make the simple proof using paperwork here, and to obtain equation number 12, which is the basis of the proposed quantum machine learning. And then by taking this is just we use the example of the 3 qubit. Yeah, 3 qubit here. So we have this position. This is for the amplitude for the cat 000, 010, 100, and 110. And then we apply Hadamard to the cat psi here. This is following the 8 identity. It is following the structure, even though this is 4, but for the demonstration we use 3. Actually, everybody can also prove using this 4, but for the simplicity we use 3 here, and you obtain this one. So this is the cat psi 0. And then because we are having the measurement for the first qubit, we use this gate, with this operator, and then we obtain the cat psi prime here. So we have this matrix, and then from this matrix we finally the results is depending on the qubit 3. For the case of the 4 qubit at the last qubit, the result will be at the last qubit. Therefore, the measurement for the qubit 3 using the cat M30 complete the algorithm. So based on this result, everybody, we can obtain the probability of B equal to 0. Yeah, is equal to this this equation. And then the next task is to prove that equation 11, this is 11, this is from the classical, should be equal to the equation 11, which is from the quantum. So we can yeah, make the mathematical modification there, and then obtain this equation number 19 and also this equation number 20. And then once you have this this equation, and then you complete the proof that 19 is equal to the 20. So it's mean that the quantum machine learning can replace the computation of the classical computation for the term mapper. So we are trying to test. So we use the 5G binary complex shift keying here. So we use the 4 qubit here, and then this is the training. So this part is used for the training, and this is for the testing, or for the real use. So we use the training and the testing simultaneously, which is not similar to the classical machine learning, where you should first train the model and then use. But for the quantum machine learning, you can use simultaneously the training and also the testing at the same time. And then yeah, we use the qubit Q1 to distinguish the training dataset XM, and the dataset to be to be tested is Y. Y is the receive signal, and then Q1 is 0 is for training XM, while Q1 is for the data. So this is for training and this for the data. And then with the sum spacing with like this, yeah, this is the careful testing, careful use of the amplitude encoding. Everybody can obtain the proof of the mathematical calculation using this one. This is actually very simple, but even though very simple, it is very surprising that it works well for the mapping of the 5G. And then everybody can also test that with this table. Yeah, with this table, you can have this state. Yeah. You have the state. So this state indicate that this is for the training and this is for the testing. And then after that, you apply. This is, for example, this is the receive signal. So we want to test this red star. It is belong to bit 0 or belong to bit 1. And then we are testing here. Yeah, we are testing here. Yeah, we put here. So 0.5 square root 2. Yeah, so we convert the classical value into the quantum state here. And then by doing that with this circuit, yeah, and then surprisingly, yeah, everybody can obtain this result. So very good point is that we do not decide this area, this region, but this algorithm, this quantum circuit can decide by themselves, and then this is very accurate. And we test with noise. With noise also, they can naturally, they can allocate, they can map bit 0 is in blue color and bit 1 is in red color. So this is very good. And then because of for the case of the complex PPSK, it works very well. And then we are interested to test for the random modulation. So this is the results of our random modulation. Oh, I almost run out of time. This is the result of the random modulation, everybody. So you can see here for the normal, normal modulation is that, sorry, I go back like this. So usually square, and this is for the classical case. It is very easy, actually very easy to decide. You just put the line here, and then based on the line you decide. But for the random modulation, it is difficult because there is no such automatic function to do that. So we are testing using this one. So this is just an example of the future modulation, and they are not following the square. So with our algorithm, with the quantum machine learning, the circuit, the quantum circuit can also distinguish, and they can also decide the bit currently being 00 because
sorry,
this is
Professor, your voice is okay.
Okay, so you can hear my voice?
Okay.
Yes, thank you. Thank you. So this is for the 2 bits, everybody. So for the 2 bits, and we intentionally do not put the symbol in the same position. But the quantum machine learning, surprisingly, they can identify and they can provide us with the good decision on the bit is either 00 or 01 or 10. So this is a very good result, and we are very happy with this this work and this algorithm. And then we are challenging also ourselves into the more random modulation. So here it is not following exactly the square modulation like what we have in the Wi-Fi 7. Wi-Fi 7 will be maybe in 2030 also. Wi-Fi 7 is expecting to use 2044, 2048 circle or dot like this or symbol. But actually, the random symbol like this is very good. It is following the Shannon expectation that random modulation give us more spectral efficiency. So we are trying to do that to achieve that dream. So we are. This is also an example of random modulation in the future. Yeah, maybe in the future we can design any figure or any form. So in this example, we test just this is 2, this is 4, and this is 2, and with the direction like this, and the position, they are not the same. So the position are not the same. For example, this is 000, 001, and 111 and 110. So we are very curious whether quantum machine learning can help us to distinguish the bit, depending on the number of qubit we are using, either 011 or 100 and etc. And surprisingly, the quantum machine learning works very well, and we can obtain the decision like this. So everybody can see here 000 is represented by the blue color here, 001 is by red, and 111 is by brown here, and all. So from this result, we conclude that this really helped us a lot to map the future expected random modulation. So the QML still work well for the random non-QM, where it is used for the modulation. And then more difficult function, usually we should use to distinguish which bit is belong to which symbol. Yeah. So more difficult function to distinguish the area of its symbol can be avoided. Sorry, this can be avoided. So by this result, I do hope that we can develop any random modulation in the future. Okay, so I would like to conclude this talk. So we have some takeaway point here. So the first, this talk has demonstrated that quantum machine learning for future any complex mapper, where 5G modulation of both real and complex symbols are used as the demonstration purpose. So we use 5G here because we are currently having the standard of 5G. But next time, maybe we can also propose the new standard for the modulation in 6G. The QML is designed to keep the computational complexity low, even though the future modulation mapping may involve thousand constellation points. And we first derive the equality of the equation based on the classical and also the quantum computations, and they are equal. It means that the validity is confirmed here. We then use the series of computer simulation to evaluate and demonstrate the effectiveness of the QML for 1,000 random complex binary specifying. We found that the proposed QML can effectively demap the CBPSK symbol by using only 4 qubits. And then in the current development, we are trying to use the less number of qubits to demap more complex and more random modulation. And then with this QML, we are expecting that virtual regions are automatically identified by the algorithm. And then we are also expecting that the design can be extended to any higher order modulation of the future modulation constellations, especially random modulations, which is theoretically excellent, satisfying the Gaussian distribution that maximizes the entropy, but currently difficult in practice. So with the development of the quantum machine learning, we are expecting that many difficult problems can be solved currently with the algorithm. Okay, so Mr. Jatmika, I think that I have presented all, so we can enrich the discussion, we can enrich the idea in the Q&A. So again, thank you very much. Halo Pak Jatmika, you still unmute?
Yes, sorry. Thank you for the fruitful discussion, Professor. So let's jump to the Q&A session. So before that, so if you have some question or some another, so you can chat in the chat room Zoom, or you can raise your hand. Okay, let's start the Q&A with the first question is, okay, how this is related to edge computing? From Mr. Soda. Thank you. Okay, maybe yes.
So I just I directly answer the question.
Yes.
Yes. Okay, so I am very happy, everybody. There are many questions. So, Mr. Jatmika, can you highlight which question I should answer first?
This one from Mr. Soda.
From Mr. Soda.
Yes. This is a reply. Sorry, I will type here. I will retype again.
Yeah, or maybe you can just
the last one.
read.
How this is related to the edge computing. The last one.
Okay. Yes. Yes. Okay. So I know that it is a simple question, but the impact is very big. Yes. I know that some idea for the future telecommunications is using the edge computing, and for the computation in the edge, they are expecting to use the quantum computer. So I think for the quantum computer and the edge computing, we can combine such that we can avoid the long distance, but the resources are available in the local. So with this first, yeah, we have to point here the combination between the intelligence and the speed. And the second is the use of the closest resources compared to the center or to the long distant resources. So I do hope that this is related a lot to the edge computing.
Thank you. Let's jump to the next question from Mr. Sunil Karki. In digital modulation, why you are using qubit instead of qubits? To tackle qubits, it's more difficult than qubits. We know qubits related to two-level system, so it will be easier.
Yes, okay. Yes, okay. Yeah, this is very good. Okay, so please let me show again our equation. Yeah. So okay. Okay. I am very happy that you understand the philosophy of this equation. So actually, we understand the problem here, that we are trying to avoid the increase of anything inside the bracket, but we are trying to increase the many factors outside of the logarithm. Why? Because when you increase this k or n or b, and then this is the you have the linear increase on c when you increase k and b, while when you increase inside, they are not linearly related. So we are trying to increase the anything outside of the logarithm, but it is difficult. Yeah. So one of the solution is that we use the level of quantum from binary or qubit into the qubit, so we can have the larger value of k here. However, in parallel to that, we are also trying to increase the something inside the bracket here. So one of the easy one is to increase the modulation. So actually, modulation and qubit not so related, but yeah, when you use the qubit to map the m here, of course the computation will be different. Yeah, but we do believe that the number of qubit will be smaller and the number of steps will be also smaller. So that is currently our vision to the future of the development of qubit. But currently we are developing qubit for the error correction and also for the cryptography, not merely on the mapping of the modulation. I do hope it answered the question. Thank you, Pak.
Okay, thank you. Okay, thank you. So for the next question from Mr. Bonnie Paul, can you kindly explain in which step quantum machine learning is used in your quantum circuit?
Okay.
Okay.
Yes. Okay, so yes, I think I should highlight also the structure here. This is I took from the Maria. So we define as what quantum machine learning is the structure. Yeah, so we have the dataset input, we have the input encoding, we have the processing, and we have the readout, and we have the output. And output here is the mapping of the binary decision of the received signal. Yeah, and then this is the different with compared to the classical machine learning. So because of these definitions, so yeah, to the best of our knowledge, we define that all circuit here, all circuit here, it form the quantum machine learning. So the structure from the quantum machine learning, and maybe for you are from the physics, you are interested in the relationship with the pattern and also with the extensions. So based on our experience, that when you increase the number of the symbol, yeah, then the structure this can be copied. Yeah, you can repeat the same with a similar pattern. So by doing that, and then you have at least the two benefits. So the first is you have some patterns, and the second is that you have simple processing, simple and faster computation. So I do hope that it answered the question. Thank you, Pak.
Thank you. Thank you very much. We still have plenty of questions. Yes, next question is from Mr. Haikal Kubi Saputra. The question is, hello, I have two simple questions. What makes good encoding? Is the couple encoding like phase amplitude possible? Yes.
Yeah, it's a typical question. Okay, so okay, so our definition, maybe you have other definition or other criterion, but according to our experience and our development currently, that we define good encoding if we do not use the number of qubit lot. So comparing to the use of the basis encoding, we are preferring the amplitude encoding. So that is the first criterion of our criterion about how we decide the good encoding. And then the second is that we can easily design the circuit, yeah, that use the simple or smaller number of the gate or processing on the step. So by those two criterion, we are expecting that currently the amplitude encoding is the best for the quantum machine learning. Thank you.
Thank you. Thank you for the answer. Okay, let's jump to the next question from Miss Michelle Pinney. I did not fully understand what is the main advantage in using quantum machine learning with respect to classical machine learning. Can it be quantified how much faster quantum machine learning is and why?
Yeah, okay. This is also very good and difficult question. Okay, so I am also expecting this question in this session. Okay, please allow me to show, or maybe this. Okay, everybody. So or maybe not this, maybe this table. Yeah, okay. So from here, the advantage of the quantum machine learning, to the best of our knowledge, first, we don't need to train first. So we can train and use simultaneously. So the first point. So for example, you go to different area, you don't need to train first because different area have different channel. So basically, if you are using the classical machine learning, you should train first because the channel in this area are different compared to the channel in another area. So, but with quantum machine learning, you can just use it because you can use simultaneously. The second, we define good computation if the number of the operation is smaller. So for example, if the number of multiplication, or especially the division, the most difficult in hardware is the number of division. If the number of division or multiplication is smaller, then our algorithm is simpler. So with quantum machine learning, we have that, and we have also parallel processing, which is not available in the classical machine learning. So this is the second motivation why we are expecting to use the quantum machine learning. The third, yeah, for the mapper, we don't need to define the function to spare it dot here, to spare it symbol. Usually, if you use the quantum machine learning, yeah, I don't know. Maybe you can modify too. But with the quantum, we can avoid the difficulty of using sparation here. And when you can demap it correctly, and then the efficiency that you get is very high. The efficiency is shown in this figure. So this is the Shannon limit. Yeah. Usually you have the shaping loss here. Shaping loss is coming from the structure of the modulation, which is usually in square. But if you can use the circular or ellipse, for example, maybe ellipse may be good, maybe circular may be good, but maybe circular is the best. Yeah. If you can use circular, and then you can minimize the loss here, which is circular is difficult in practice because of the decision of the area. So this is to the best of my knowledge currently, that quantum machine learning is the new very good news for the mapping of the telecommunication. I do hope it answered the question.
Okay, thank you for the nice answer. So let's jump to the next question from from Mr. Vijay. So please discuss any potential challenges encountered during development and how they will address, and include a high level of a view of the quantum machine learning architecture used in your application.
Yeah. Okay. This is very good question. So everybody, that okay, so there are at least 2 points to answer this one. So the first is in here. Yeah, in here, in the current 5G advance, we have the classical machine learning. The classical machine learning here is used to replace the existing or the traditional computation. For example, with the BCGR algorithm, we can replace using this machine learning here. The problem is that if the number of users are increasing, yeah, and then you have to detect them with the correct and faster. The prediction of the future use of the number of users is not only human, but also the sensor or devices. So the computation in the future is also challenging as the number of users is increasing. This is the first. The second, the networks, the core of the network should manage the traffic, as good as possible, and also predicting the security, and also many things to avoid the congestion. So this is requiring machine learning here. So this is in the classical way. But as the number of increasing, and also the require security, we are having the quantum key distribution. Here. This is a very, very challenging and also very promising technology. So we may need to change. First, the medium is changing from the classical to quantum channel. And then with the change of the QKD, and then why don't we also change the quantum machine learning, the computation too, into the quantum machine learning? So when we apply the new devices here, we replace both. We replace the speed of the computation, and also we put the security. So by doing that, I think the quantum machine learning, quantum, and also other quantum algorithm, quantum cryptography, quantum searching algorithm, for example, they will be useful in the future. So this is what is our current view on the direction of the future telecommunication with the coming of the quantum algorithm. I do hope it answered.
Okay, thank you. So before I jump to the next question, so I remind you, if you have some question and directly talk to Professor Hairul, you can raise your hand. Okay, the next question is from Mr. Itoen Okon. The question is, quantum encoding is done by using the basis eigenstate of regular Schrödinger wave equation. Why not consider encoding using direct equation, where the speed of particles can be of close approximation to the speed of light? Thank you.
Yeah. Okay, so this is also very good idea, I think. But what currently we are developing is starting from the simple one, and then it is practical. So we are thinking currently the amplitude encoding is simple and also practical. But if in the future we have another type of encoding, and that is also applicable and also can be synchronized with the current development of the telecommunication, I think it is a good chance and also a good opportunity. So I think we will accept, and the society will accept better idea in the future if it is practical. So I do hope it answered the question.
Thank you. Thank you very much. So please still bear with us. So we have some plenty of question. The next question is from Mr. Sunil Karki. How properly Grover algorithm is working here in database search?
Okay, yes.
Okay, thank you.
I am also expecting this question. Okay, thank you, Professor Sunil. So I don't know the Grover search algorithm, but okay, I should show the structure of the telecommunication. Maybe we can take insight from there. So here, actually, the Grover search algorithm can be applied for, first, of course, for the breaking of the cryptography. Yeah. But for the beside of the cryptography, you can also apply for the modulation if you are trying to find the header, because in the telecommunications, one of the big problem is the synchronizations. In the case of the synchronization, we do not know the header. So if we do not know the header, all bit you take will be wrong. So maybe this is just the short thinking that maybe we can also apply the Grover search algorithm to find the header of the block. Yeah, because usually this is the big challenge in practical. And the first is for cryptography and the finding of the header, and then the third, this is for the multiple access. Of course, for the case of the multiple access, we can use the entanglement. So the entanglement is expected to increase the user rate of the mobile communications between user 1 and user 2. The rate will be increasing if we entangle them. And but maybe with the quantum Grover search algorithm, we can find the users having the highest power. So when you can find the users having the highest power, then you can use, for example, successive interference cancellations, and you can successfully decode all users with the perfect mean, with the best or with the minimum error. So this is one possibility of the quantum search algorithm in the case of the multi-user detections. So I think that there will be many applications of such kind of such algorithm beside many number of users, including human and also the devices in the future. I do hope it answered the question of Professor Sunil. Thank you.
Okay, thank you for the nice answer. So maybe this is the last question from Mr. Mona. The question is, thank you for your insightful presentation. I have a question regarding the evaluation metrics used in quantum machine learning. In addition to traditional metrics like accuracy and F1 score, could you discuss the role and significance of quantum-specific metrics in evaluating the performance of quantum models?
Oh, yes.
Thank you.
This is very good question. So yes, our lab is currently working on the two quantum algorithm. We are working on the classical machine learning, basically for the error correction code. We are developing the redless coding with the reinforcement learning. And for the case of the classical machine learning, so we are facing the problem of the giving the training with the correct SNR. SNR is standing for the signal to noise power ratio. So once, this is in our field. Once you find the good data training for the correct SNR, and then the algorithm will work for any position. I mean any position mean any SNR. So that is the challenge of the classical machine learning currently we are facing. But for the quantum machine learning, I think this is still open problem, because in our algorithm, we put here, we are actually still also working on that. Wait. We put, okay, this is the classical. Yes, here. Why here? Why here is still contain noise. And the noise here, we do not identify yet whether the problem of the classical is also appearing the same as in the quantum. But yeah, this is my prediction is that they works differently. Why? Because we in the quantum we have the parallel processing, so the noise of the data training will be involved in with, and not the noise of the noise of the testing will be used together, yeah, with the noise with the real noise of the testing, which is not happening in the classical. Here, yeah. So here, usually here contain noise. This one contain noise. Yeah. And the training also, of course, they have noise here, but in the classical one, we separate training and testing. But in the quantum, we use both. That's why I think the impact will be different. But we do not complete it yet, and we decide that this is still open. So if everybody are interested to work on that, I think it is also very good observation and very good investigation on the good model for the quantum machine learning. Maybe you can put another model beside, I mean, at the right hand side of this circuit. I do hope it answered.
Okay, thank you for the nice answer. So is there any last question? Maybe I will check the Discord if there any question. Or maybe same with the chat room. So if you want to ask in more detail, you can write in the Discord channel. on the Keynote 2. So you can write maybe for 3 days ahead. So you can keep in touch with Professor Khairul. Okay, thank you for the fruitful discussion and your time, Professor. So
Thank you very much, Dr.
we-
Chatmika and everybody. So I do hope you enjoy the workshop and we can take many insight and also good collaboration, good networking. Inshallah. Thank you very much. Yeah.
Okay, thank you very much. Okay. So this is the last session of the first day. So you can join in the second day at the exact time tomorrow, and please be careful with the time zone. So, and the tomorrow we start on the exact time. Okay, thank you very much. I will end in this session and return to the organizer. Thank you.
Thank you very much, Pak Chatmika. So
Thank you very much.
I do hope that tomorrow we can meet again with at around 3 o'clock in Indonesia time.
3 o'clock.
Yeah,
Yes, 3 o'clock.
Okay, so thank you. Goodbye, everybody.
Okay, thank you.
Yeah,
Thank you. See you later.